Hello there, and welcome to the Sleep Porch. Tonight, we'll be exploring one of the most astonishing creations humanity has ever assembled: the periodic table. At first glance, it looks calm and orderly, a grid of symbols and names. But beneath that still surface lies a story that stretches from the birth of the universe to the very edge of what's possible. This is a map of matter itself. It is a quiet catalogue of everything that can be created, everything that can be undone, and everything that appears only for the briefest instant before fading away. Some of what rests within it becomes stars and oceans. Some shapes bones, breath, and thought. And some does not arise naturally at all, coming into being only when human curiosity stretches reality beyond its familiar boundaries. This is not just chemistry. It is a quiet tour through stability and chaos, permanence and decay, creation and destruction. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let your eyes grow heavy and allow curiosity to soften your mind. Let's begin. More than half of the periodic table consists of elements that do not naturally exist on Earth. When you look at the familiar grid, it is tempting to imagine that every square represents something you could, in principle, dig up somewhere on our planet. But a huge portion of the table is made of elements that are simply not part of Earth's natural inventory in any lasting way. Many are so unstable that even if they were present when the solar system formed, they would have decayed away long before oceans cooled or rocks hardened. What is left is a kind of selective survival story. Nature keeps only the elements that can endure. Everything else is either fleeting or must be continuously made by extraordinary processes. That means the periodic table is not only a list of what exists, it is also a list of what fails to persist. And the mind-bending part is that humans have still managed to meet some of these missing elements face to face. Not by finding them, but by making them. It is like discovering animals that cannot live in the wild. Then building a habitat so precise they can exist for a moment, just long enough to be known. Some elements on the periodic table exist for less than a heartbeat before falling apart. There are atoms so short-lived that the very idea of holding them feels absurd. Their nuclei are built on a knife edge, and the moment they come into being, they begin unraveling. Yet we still treat them as real members of matter's family because they leave unmistakable signatures behind. A single atom can announce itself through a cascade of changes. A sudden particle emitted, a burst of energy, a daughter nucleus appearing in its place. In some experiments, the proof of existence is not a sample you can weigh or a powder you can bottle, but a tiny sequence of events that happens in a detector, like a brief whisper followed by silence. It is a strange kind of knowledge, more like tracking a rare animal by footprints than meeting it directly. What makes it feel even more uncanny is the contrast with everyday objects that seem solid and permanent. Your table, your walls, your bones feel stable because their atoms occupy longivited arrangements. But the periodic table also includes matter that cannot settle, matter that is born already in the act of disappearing, as if the universe allows it only a fleeting glance. The periodic table contains elements that were created only once and never again. Some members of the table have appeared in history under conditions so specific that the event itself has never been repeated in quite the same way. In these rare moments, nature and technology align to form nuclei that are not part of any ongoing cycle. They are not produced steadily in stars like common building blocks, and they are not replenished by slow geological processes. Instead, they arrive as a one-time consequence of an extreme chain of reactions, then vanish into new forms. The astonishing idea is that the evidence for such an element can be thinner than a breath. It might be a few atoms embedded in debris, or a short trail of transformations that points back to a parent nucleus that is already gone. This turns the periodic table into something like an archive of singular events. Not just a catalog of substances, but a record of moments when the universe briefly visited a possibility and then moved on. It also reveals a subtle limit of human control. We can plan, build, and aim our experiments with immense precision and still find that some kinds of matter are so difficult to create that they become historical accidents. A square on the table can represent not a resource, but a once-only footprint in time. The periodic table reveals strict limits on how large an atomic nucleus can be. A nucleus is an uneasy compromise. Protons want to push one another apart because they carry the same electric charge, and that repulsion grows stronger as you pack in more of them. Neutrons help by adding attraction through the strong nuclear force. But that force is powerful only at extremely short distances, and it does not scale up gently like gravity does. As nuclei grow, they become like overfilled structures held together by forces that work only when everything is pressed tightly into place. Past a certain point, the balance becomes so strained that the nucleus can split or spit out a chunk of itself or shed energy in ways that quickly change its identity. This is why there is no endless climb toward heavier and heavier stable matter. The periodic table ends not because we ran out of imagination, but because the laws of nuclear binding set hard boundaries. What feels mind-blowing is that these boundaries are not arbitrary. They emerge from the same deep rules that govern particles and forces everywhere. In other words, the table has an edge because reality has an edge. And by studying where that edge lies, scientists are not merely adding squares to a chart. They are probing the architecture of the strong force itself, testing how close matter can approach collapse while still counting as an atom. Entire regions of the periodic table are dominated by radioactive decay rather than chemistry. For many elements, the most important story is not what they bond with or what color their salts might be, but how they transform from the inside out. In these regions, the nucleus is so eager to change that chemical behavior becomes almost secondary. An atom can be part of a compound, locked into a crystal, sealed inside a metal, and yet its identity can still shift without asking permission from its electrons. That is a stunning inversion of what we usually mean by matter. Normally, we think chemistry determines an object's fate. Here, nuclear change rewrites the object from within. This is why certain parts of the table feel less like a chemistry set and more like a landscape of internal clocks, each ticking at its own pace. Some nuclei release energetic particles. Some emit penetrating light. Some reorganize by converting one kind of particle into another. Those changes can produce heat, create new elements, and leave behind telltale traces that can persist in minerals and materials. It is also why handling these substances demands such care. Their danger is not namely about burning skin or corroding metal. It is about invisible energy that can pass through ordinary barriers because the action is happening at a deeper layer than chemical reactivity. The periodic table shows that stability is rare and instability is the default. It feels natural to assume that most atoms are content to exist. After all, nearly everything around you is made of atoms that endure. But when you zoom out to include all known possibilities, the calmness of common matter becomes the exception. The majority of combinations of protons and neutrons do not settle into lasting arrangements. They decay, fragment, or rearrange into more stable forms. This means the stable elements we build our world from are like survivors clustered in a small oasis within a vast desert of unstable nuclear configurations. And that reorders your sense of what is normal. The familiar materials of daily life are not the typical outcome of matter. They are the fortunate outcome. Stability requires very specific balances of forces, energy levels, and internal structure. When those balances are not met, nuclei do not politely persist. They change. This rarity also carries a strange comfort. It implies that the atoms in your body, your home, your air, are sitting in unusually secure valleys of possibility, sheltered from the constant urge to transform. At the same time, it gives the periodic table a hidden drama. Each stable element is not merely a label, it is a solution to a difficult problem nature usually fails to solve. Some boxes on the periodic table represent matter that can only exist inside particle accelerators. There are elements that do not come from mines, meteorites, volcanoes, or even the deep interior of stars in any steady way we can harvest. They appear only when we build machines that can fling atomic nuclei at one another with extraordinary precision and energy. In these experiments, the aim is almost poetic in its difficulty, to make two nuclei touch and merge long enough to become a new nucleus rather than ricochet apart. The odds can be so low that days of work might produce only a few successful creations, each one signaled by a tiny flash of evidence in a detector array. And yet, that is enough, because physics has taught us how to read those flashes like a language. What makes this truly mind-blowing is the level of control. You are steering the birth of a new kind of matter, atom by atom, by shaping beams, targets, magnetic fields, and timing systems so accurately that a single successful collision can be recognized among countless failures. These elements are not industrial substances. They are scientific messages. Each one tells us how nuclear forces behave at the extremes, and whether the periodic table has hidden pockets of longer-lived matter still waiting to be reached. The periodic table encodes which elements can form planets and which cannot. Planets are not made from a random grab bag of elements. They are the outcome of sorting rules that begin in hot gas, dust, and cooling disks around young stars. Some elements eagerly condense into solid grains at high temperatures, becoming the seeds of rocks that can clump, collide, and grow. Others stay gaseous until temperatures are far lower, or they prefer to remain as volatile compounds that drift away with the solar wind. This means the periodic table contains a quiet instruction manual for planet building. Elements with strong tendencies to form sturdy solids become the backbone of crust and mantle. Elements that dissolve into metal phases sink inward and shape a planet's core. Elements that remain volatile can dominate atmospheres, oceans, and ices, but often in very different places depending on distance from the star. What feels astonishing is that this is not just a story about Earth. It is a universal filtering process. Two worlds can form from the same primordial cloud and end up radically different because of how temperature gradients, pressure, and chemistry select which elements become permanent architecture and which remain fleeting passengers. In that sense, the periodic table does more than list matter. It offers a glimpse into the kinds of worlds that matter is capable of forming. Some elements on the periodic table exist in quantities so tiny that they have never been directly observed. A few are so rare that no visible piece of them can be pointed to, even with the most advanced laboratory instruments. Their total presence on Earth may amount to less than a single visible speck, dispersed thinly through immense volumes of rock, air, and water. In those cases, scientists often know an element is present, not because they can isolate it in a vial, but because nature leaves indirect clues. A parent nucleus decays and produces a characteristic daughter. A distinctive pattern of energy appears in a detector. A faint spectral fingerprint shows up in a carefully analyzed signal. The element becomes real through evidence rather than through possession. That is a remarkably modern kind of reality, where existence is established by consistent traces instead of by direct display. It also reveals how strange the boundary is between the macroscopic and the atomic. A single atom is perfectly real, with mass, charge, and structure. Yet, if there are only a handful of atoms spread across the entire planet at any given time, the element becomes more like a rumor. The universe occasionally confirms the periodic table makes room for these near-invisible residents, reminding us that matter is not only what is abundant, but also what is merely possible. The periodic table marks the boundary between ordinary matter and exotic nuclear physics. Most of the substances you encounter are governed by electrons arranging themselves around a nucleus, building bonds, making solids, liquids, and gases. But at the far edges of the table, the story shifts. The nucleus itself becomes the main character, and its internal structure starts behaving in ways that feel less like chemistry and more like a new form of architecture. Shell effects can appear that reshape expectations, allowing certain combinations of protons and neutrons to hold together longer than nearby neighbors. Other combinations stretch toward extremes of neutron richness or proton richness, where familiar patterns break and new decay modes dominate. In this territory, the periodic table becomes a testing ground for models of the strong force, for the interplay of energy levels inside the nucleus, and for the subtle rules that decide whether a nucleus can exist as a coherent object at all. What makes this boundary so fascinating is that it connects to the most extreme places in the cosmos. Conditions that are unreachable in ordinary materials can be approached in stellar explosions and in the crushed matter of compact stars. So the table is not only a chart for classrooms, it is a frontier line. Cross it, and you are no longer asking how atoms bond. You are asking what it means for matter to be stable in the first place. Hydrogen began forming before stars ever existed. In the earliest moments, after the universe cooled enough for particles to combine, hydrogen was already taking shape. Long before there were galaxies, planets, or even the first stars, simple hydrogen atoms were drifting through expanding space. This makes hydrogen not just the lightest element, but the oldest form of ordinary matter that still surrounds us today. Every glass of water and every living cell contains atoms that trace their lineage back to that quiet, ancient era. What is especially striking is that hydrogen did not need stars to exist. Stars need hydrogen.
Gravity gathered immense clouds of it, compressed them, and ignited nuclear reactions that would later create heavier elements. But hydrogen itself was there first, patiently waiting. This gives hydrogen a unique role in cosmic history. It is both the beginning and the fuel.
Even now, vast regions of space are filled with cold hydrogen gas that has never been part of a star. When you look at hydrogen on the periodic table, you are looking at a survivor from the universe's earliest chapter, a substance that has watched everything else arrive later. Helium carries a permanent signature of the birth of the universe. Helium is often thought of as something found in balloons or laboratory tanks, yet its truest story is written across the vastness of the cosmos. Much of the helium that exists today was not forged inside stars, but formed during the universe's earliest moments, alongside hydrogen itself. The conditions of that ancient era set a precise balance between helium and hydrogen, a ratio that has endured across time and still quietly shapes what astronomers observe in the universe today. No matter where you look in the universe, from distant galaxies to nearby clouds of gas, the background amount of helium follows that ancient pattern. Stars certainly make additional helium by fusing hydrogen in their cores, but they add to an existing baseline rather than creating it from scratch. This makes helium a kind of cosmic fossil. Its abundance is evidence that the universe really did pass through a hot, dense beginning. Without helium behaving exactly as it does, many stellar processes would unfold differently, and long-lived stars like the Sun might never have formed. So helium is not just a byproduct of stars. It is a quiet confirmation that the universe has a memory, and that memory is still measurable today. Lithium is one of the few elements that the universe struggles to make. Lithium occupies a strange and lonely position in cosmic chemistry. Despite being lighter than many common elements, it is surprisingly scarce. The processes that made hydrogen and helium in the early universe produced only tiny amounts of lithium, and stars tend to destroy it rather than create more. When lithium finds its way into stellar interiors, it is often broken apart instead of being preserved. This means that lithium must rely on rare and indirect pathways to exist at all. Some of it forms during violent cosmic events where energetic particles shatter heavier nuclei into lighter pieces. Some appears in the aftermath of stellar explosions, but even then, it is fragile. The result is that lithium becomes a tracer of unusual processes rather than a routine building block. Its scarcity has puzzled scientists for decades because theoretical predictions and observed amounts do not always agree. That mismatch suggests there are still gaps in our understanding of how matter behaved in the early universe and inside stars. On the periodic table, lithium looks modest and simple. In reality, it is a reminder that not all elements are equally welcome outcomes of cosmic evolution. Beryllium is fragile in stars, yet crucial for understanding cosmic collisions. Beryllium has a delicate nature that makes it almost allergic to the conditions inside stars. When exposed to the high temperatures and pressures of stellar interiors, beryllium nuclei tend to break apart rather than fuse into something heavier. This means stars are not efficient factories for beryllium. Instead, much of the beryllium found in the universe is thought to form when high-energy particles slam into heavier atoms in space, shattering them like glass. These collisions occur when shock waves from stellar explosions accelerate particles to enormous speeds. In that chaos, nuclei fragment and beryllium emerges as one of the pieces. Because of this origin, beryllium acts like a record of ancient violence. Its presence in old stars and cosmic material can reveal how active and energetic the environment was when those objects formed. Unlike elements forged quietly in stellar cores, beryllium carries the imprint of impact and disruption. It is an element whose existence depends on destruction, making it a subtle witness to some of the most energetic processes the universe has ever seen. Boron exists because the universe breaks things apart. Boron is another element that owes its existence less to construction and more to demolition. Stars are excellent at building many heavier elements, but boron does not survive well in their interiors. Instead, boron forms primarily when energetic particles smash into larger nuclei, such as carbon or oxygen, and fracture them. This process turns destruction into creation. It means that boron abundance is tied to how often matter is exposed to high-energy collisions, rather than to how long stars have been burning. In a sense, boron measures the violence of cosmic history. Regions of space that have experienced more energetic particle bombardment tend to show higher boron levels. This gives boron a unique role as a chemical storyteller. It whispers about past shock waves, exploding stars, and roaming high-energy particles that no longer exist. On Earth, boron becomes quietly important in chemistry and biology, but its cosmic origin remains dramatic. Each boron atom is evidence that somewhere, sometime, a larger atom was struck hard enough to splinter, and that the universe found a way to reuse the debris. Carbon can bond in more ways than any other element. Carbon's true power lies not in its abundance, but in its versatility. A carbon atom can link to other carbon atoms in long chains, branching networks, flat sheets, and closed cages. It can form strong bonds that are stable yet flexible enough to be rearranged into countless structures. No other element matches this range of possibilities. This bonding freedom allows carbon to create everything from simple gases to complex molecules that can store information, catalyze reactions, and build living systems. What makes this even more astonishing is that carbon does this while remaining relatively small and manageable at the atomic scale. Its electrons sit at just the right energy levels to allow bonds that are neither too rigid nor too weak. This balance is rare. If carbon behaved slightly differently, the chemistry of life as we know it would not be possible. The periodic table places carbon near the center of many chemical trends, and for good reason. It is not just another element. It is a master builder capable of exploring an enormous landscape of molecular forms, while still obeying the quiet rules of atomic physics. Nitrogen quietly governs the chemistry of life and air. Nitrogen makes up most of the air you breathe, yet it rarely draws attention because it is so reluctant to react. Its atoms pair up into molecules held together by extremely strong bonds, creating a stable background gas that does not easily interfere with other substances. This apparent inactivity is precisely what makes nitrogen so important. It creates an atmosphere that dilutes oxygen, moderates combustion, and allows life to exist without constant fire. At the same time, nitrogen becomes indispensable once it is incorporated into living systems. It forms part of the molecular backbone of proteins and genetic material, helping store instructions and enable growth. The challenge is that most organisms cannot use atmospheric nitrogen directly. It must first be transformed by specialized microbes or industrial processes into more reactive forms. This quiet, gatekeeping role means nitrogen controls the pace of life's chemistry. Too little accessible nitrogen and ecosystems starve. Too much, and they destabilize. On the periodic table, nitrogen may seem unassuming. In reality, it is a regulator that balances stability and change on a planetary scale. Oxygen reshaped the entire planet long before humans existed. Oxygen was not always a dominant part of Earth's atmosphere. For a vast stretch of early history,
Oxygen was scarce, and life thrived without it. Then, certain organisms began releasing oxygen as a byproduct of capturing energy from light. Over immense spans of time, oxygen accumulated and transformed the planet. It reacted with minerals, changed ocean chemistry, and eventually filled the atmosphere. This shift altered which forms of life could survive and opened the door to entirely new metabolic strategies. Oxygen's high reactivity allowed organisms to extract far more energy from food, supporting larger and more complex bodies. At the same time, oxygen created new challenges. Its tendency to steal electrons makes it corrosive and dangerous in excess. Life had to evolve defenses against its damaging effects. This dual nature makes oxygen a powerful agent of change. It is both a resource and a threat.
The periodic table captures oxygen as a simple entry, but its planetary impact is anything but simple. It turned Earth into a world where complexity could flourish, while also imposing strict constraints on how life must operate. Fluorine is so reactive, but it challenged chemists for generations. Fluorine has an almost unmatched appetite for electrons, making it eager to react with nearly anything it encounters. This extreme reactivity makes it extraordinarily useful once controlled. But it also made fluorine notoriously difficult to isolate. Early attempts to study it often ended in failure or injury, because fluorine attacked containers, tools, and even the chemists themselves. It was only after careful experimentation and clever design that fluorine was finally tamed. What makes fluorine fascinating is that its reactivity does not come from instability, but from a very specific electronic configuration that drives it to complete its outer shell. When fluorine bonds, it forms some of the strongest chemical connections known, creating compounds that can withstand heat, corrosion, and chemical attack. These properties have made fluorine essential in applications ranging from medicine to material science. On the periodic table, fluorine sits quietly among other elements. In practice, it represents a lesson in extremes, showing how small differences in atomic structure can lead to dramatically different behavior. Neon glows only because of how its electrons refuse to bond. Neon is famous for its brilliant glow. Yet that light appears only under special conditions. Neon atoms are remarkably satisfied with their electron arrangements and have little interest in forming bonds. This reluctance makes neon chemically inert under most circumstances. However, when energy is supplied in the form of an electric discharge, neon's electrons can be pushed into higher energy states.
As they relax back down, they release light at very specific wavelengths, producing the characteristic reddish-orange glow. This light is not a sign of chemical change, but of electronic transitions happening within isolated atoms. Neon's behavior reveals an important truth about the periodic table. Not all elements express themselves through reactions and compounds. Some reveal their nature through light alone. Neon's unwillingness to bond also means it remains unchanged over long periods, drifting through space and laboratories alike. It is a reminder that stability can take the form of solitude. In the grand scheme of matter, neon shows that sometimes the most striking displays come from atoms that prefer to remain alone. Sodium transforms violently when it meets water for deeply fundamental reasons. Sodium is often introduced as a dramatic classroom example, but the spectacle hides a deeper story about energy and balance.
A sodium atom holds onto its outermost electron very loosely. Water molecules, on the other hand, are excellent at stabilizing free charges. When sodium meets water, it quickly releases its outer electron into the surrounding liquid. This sudden exchange sets off a quiet but powerful chain of events. The freed electron rushes through the water, warming it, breaking molecules apart and releasing hydrogen gas. At the same time, the sodium atoms become positively charged and immediately seek balance, joining with components of the water to form more stable compounds. What looks like an explosion is actually the system rushing toward a lower energy state. The reaction happens so fast that heat and gas are released faster than they can dissipate, creating flames and flashes. This behavior is not a quirk of sodium alone. It reflects a fundamental rule of chemistry, that atoms are driven by the search for stable electronic arrangements. Sodium simply sits at an extreme end of that tendency, making the underlying physics impossible to ignore. Magnesium once lit ancient skies and still powers stars. Magnesium has played a role in human experience for far longer than most people realize. When magnesium burns, it emits an intense white light, bright enough to illuminate night skies. This property made it invaluable in early photography and signaling, where controlled flashes could briefly turn darkness into day. That same release of light comes from electrons jumping between energy levels as magnesium atoms react vigorously with oxygen. But magnesium's story does not end on Earth. In stars, magnesium is forged during advanced stages of nuclear fusion, when lighter elements are assembled into heavier ones under extreme pressure and heat. Its presence in stellar spectra helps astronomers understand the life cycle of stars and the chemical evolution of galaxies. Magnesium also becomes part of rocky planets, contributing to minerals that shape crusts and mantles. In this way, magnesium connects human technology, stellar interiors, and planetary geology. It is an element that bridges scales from handheld flashes to the slow glow of stars, all through the same underlying atomic behavior. Aluminum was once more valuable than gold. It is hard to imagine now, but aluminum was once considered a rare and precious metal. Although aluminum is abundant in Earth's crust, it is tightly bound within minerals and extremely difficult to extract without large amounts of energy. Before efficient methods were developed, producing small amounts of pure aluminum required complex chemical processes, making it more expensive than gold. Objects made of aluminum were treated as luxury items, prized for their lightness and resistance to corrosion. The turning point came when new techniques allowed aluminum to be separated from its O's using electricity. Suddenly, what had been rare became commonplace. This shift transformed transportation, construction, and packaging almost overnight. Aluminum's low density and strength made flight more practical, while its resistance to rust extended the lifespan of countless structures. The story of aluminum shows how an element's value is not fixed by nature alone, but by human ability to access and manipulate it. The periodic table holds many such quiet revolutions waiting to happen. Silicon forms the backbone of both rocks and computers. Silicon occupies a remarkable position in the periodic table, one that allows it to bridge geology and technology. In nature, silicon readily bonds with oxygen to form silicates. The vast family of minerals that make up most of Earth's crust, mountains, sand, and clay, are all shaped by silicon-based structures that are stable over immense spans of time. Yet, silicon's electronic properties also make it ideal for a completely different role. When purified and carefully structured, silicon can control the flow of electrons with exquisite precision. This ability allows it to act as a switch, turning electrical currents on and off in response to tiny signals. That same atom, which locks itself into rigid mineral frameworks, can also enable logic, memory, and computation. The dual life of silicon is not an accident. Its position among the elements gives it just enough flexibility to form strong bonds, while still allowing its electrons to be nudged into useful motion. Few elements so perfectly connect the ancient solidity of rocks with the abstract world of information. Phosphorus glows because it stores energy in its bonds. Phosphorus has an unusual relationship with energy. Certain forms of phosphorus can slowly release stored energy as visible light, producing a faint glow in the dark. This phenomenon fascinated early observers and gave rise to myths long before its chemical explanation was understood. At the atomic level, the glow comes from electrons relaxing after being excited by energy trapped in the element's bonds. This same capacity to store and release energy makes phosphorus indispensable to life. In living cells, phosphorus atoms sit at the heart of molecules that act as energy carriers, moving chemical potential from one reaction to another. These molecules are constantly built and broken, allowing organisms to manage energy flow with remarkable efficiency. Phosphorus therefore links a ghostly glow in the dark to the invisible processes that power muscles, thoughts, and growth. On the periodic table, phosphorus may seem unassuming. In reality, it is one of the key elements that allows energy to be packaged, transported, and released in controlled ways. Sulfur bridges biology, volcanoes, and alien worlds. Sulfur is an element of contrasts. It appears in the smell of volcanic gases, the structure of certain minerals, and the chemistry of living cells. In biology, sulfur atoms help stabilize the folded shapes of proteins, allowing them to perform precise functions. In geology, sulfur compounds emerge from deep within the planet, carried upward by molten rock and released into the atmosphere. These same compounds can shape climate and surface chemistry. Beyond Earth, sulfur has been detected on other worlds, sometimes in startling abundance. Some moons and planets show signs of sulfur-driven chemistry, but hints at environments very different from our own. Because sulfur can exist in many oxidation states, it participates in a wide range of reactions, acting as a flexible intermediary between energy-rich and energy-poor conditions. This adaptability makes sulfur a kind of chemical translator, capable of linking processes across vastly different environments. Its presence ties together life, planetary activity, and the search for chemistry beyond Earth. Chlorine exists in forms that both sustain and destroy life. Chlorine's reputation often swings between helpful and harmful, and both views are justified. In its ionic form, chlorine becomes an essential part of salts that regulate fluids in living organisms. These ions help maintain electrical balance in cells and play a role in nerve signaling. Without them, basic physiological processes would fail. Yet, chlorine can also form highly reactive compounds that disrupt biological systems, damage tissues, and interfere with vital chemistry. This dual nature comes from chlorine's eagerness to gain an electron, a trait that can either stabilize systems or tear them apart, depending on context. Chlorine's chemistry reminds us that toxicity is often a matter of form and dosage, rather than essence. The same element that helps maintain life's delicate balances can become dangerous when placed in a different molecular setting. The periodic table does not label elements as good or bad. Chlorine shows how behavior emerges from relationships, not from the atom alone. Argon hides in plain sight despite being everywhere. Argon makes up a significant portion of the air, yet it rarely enters human awareness. This invisibility is not due to scarcity, but to reluctance. Argon atoms have complete outer electron shells, leaving them with little incentive to react with other elements. As a result, argon drifts through the atmosphere largely unchanged, neither supporting life nor interfering with it. Its presence is revealed mainly through careful measurement or specialized uses.
In industry and science, argon becomes valuable precisely because of its inertness. It provides protective environments where sensitive materials must be shielded from reactive gases. Argon also fills certain lighting systems where it helps control electrical behavior without participating chemically. The quiet role of argon highlights an important idea. Not all elements make themselves known through action. Some shape the world by refusing to act at all, creating stable backgrounds against which other processes can unfold. Potassium helps electricity flow through living cells. Potassium plays a central role in one of the most remarkable feats of biology, the controlled movement of electrical signals through soft tissue. Living cells carefully maintain different levels of potassium inside and outside their membranes. This quiet imbalance creates an electrical potential, a stored difference that can be released and restored with remarkable precision. When tiny channels in the cell membrane open or close, potassium ions flow in response, gently shifting the cell's electrical state and allowing life signals to move forward. This process underlies nerve impulses, muscle contractions, and even the rhythms of the heart. What makes this astonishing is the scale. The same principles that govern batteries and circuits operate inside microscopic structures using individual ions instead of wires. Potassium's size and charge make it particularly well suited for this role, fitting snugly into biological channels that exclude other ions. On the periodic table, potassium is just another alkaline metal. In living systems, it becomes a key player in the language of electricity that allows bodies to sense, move, and respond. Calcium builds structures that move and remember. Calcium is often associated with bones, but its influence reaches far beyond structural support. In skeletal tissue, calcium compounds provide rigidity and strength, allowing bodies to stand, walk, and protect vital organs. Yet calcium also operates at much smaller scales, acting as a signaling ion inside cells. Brief changes in calcium concentration can trigger muscle contraction, initiate communication between neurons, or activate complex biochemical pathways. In this way, calcium links stability with motion. It builds frameworks that endure, while also enabling rapid, reversible actions that depend on precise timing. Calcium ions even participate in processes related to learning and memory, where controlled signaling helps modify connections between nerve cells. The same element that hardens bone also helps encode experience. This dual role reflects calcium's unique chemical properties, allowing it to form stable solids and yet remain mobile and responsive when dissolved. The periodic table places calcium among familiar metals, but its true reach spans from the solidity of skeletons to the fleeting patterns of thought. Scandium behaves like a missing puzzle piece in the periodic table. Scandium sits in an unusual position where trends seem to hesitate and restart, which is why it often feels like a connector rather than a standalone star. Its chemistry overlaps with neighboring elements in ways that blur boundaries, making it difficult to classify by simple behavior alone. This gives scandium the role that is subtle but revealing. By studying how it reacts, scientists can see where one family of elements gives way to another. Scandium's ions are small and highly charged, which allows them to influence crystal structures and strengthen materials even when present in very small amounts. In alloys, scandium can dramatically improve strength and resistance to deformation without adding much weight. This disproportionate effect makes scandium feel like a keystone, an element whose presence brings coherence to systems that otherwise behave less predictably. Its rarity and concentrated form also adds to its mystique. Scandium is not absent, but it is dispersed, hiding within other minerals. That scarcity mirrors its conceptual role. It fills a gap in understanding, rather than dominating attention, helping the periodic table make sense of itself. Titanium combines lightness and strength in ways that seem contradictory. Titanium challenges everyday assumptions about metals. It is as strong as many steels, yet significantly lighter, creating a combination that feels almost paradoxical. This arises from the way titanium atoms bond with one another, forming a lattice that resists deformation while avoiding excessive density. Titanium also has a remarkable resistance to corrosion. When exposed to air, it forms a thin, stable oxide layer that protects the metal beneath without flaking away. This self-shielding behavior allows titanium to survive harsh environments. From seawater to the interior of the human body, its compatibility with living tissue has made it invaluable in medical implants, where strength and stability are essential, but weight and reactivity must be minimized.
On a larger scale, titanium's properties have reshaped engineering, enabling lighter aircraft, more efficient spacecraft, and durable structures that push performance limits. Titanium shows that atomic arrangement can overcome trade-offs that seem unavoidable, producing materials that feel almost intelligently designed despite arising from simple physical rules. The nadium stabilizes structures at both atomic and planetary scales. The nadium rarely takes center stage, but it excels at reinforcement. At the atomic level, the nadium atoms slip into metal lattices and alter how layers slide past one another. This makes materials tougher, more resistant to fatigue, and better able to withstand repeated stress. A small addition can dramatically change how a structure behaves under pressure. That same stabilizing influence extends far beyond engineered materials. Vanadium appears in minerals that form under specific geological conditions, offering clues about the chemical environment deep within Earth. Its different oxidation states allow it to act as a chemical buffer, moderating reactions and maintaining balance in complex systems. In some planetary contexts, vanadium helps trace the history of volcanic activity and mantle processes. The element's versatility comes from its willingness to adopt multiple electronic arrangements, adjusting to its surroundings rather than imposing a single behavior. Vanadium's quiet adaptability makes it a stabilizer across scales from microscopic lattices to the slow churn of planetary interiors. Chromium creates color by rearranging light itself. Chromium's most striking contribution to the world is visual. When chromium atoms are incorporated into certain minerals or compounds, they alter how light is absorbed and emitted. This happens because chromium's electrons can occupy energy levels that interact strongly with visible wavelengths. In some arrangements, chromium absorbs specific colors and reflects others, producing vivid greens, reds, and deep purples. These colors are not surface effects or coatings. They arise from the internal electronic structure of the material itself. This is why chromium can give gemstones their distinctive hues, and why chromium-based compounds appear in pigments and finishes that remain stable over time. Beyond aesthetics, chromium's electronic flexibility also underlies its role in corrosion resistance. When added to steel, chromium forms protective layers that change how light and air interact with the surface, reducing chemical attack. Chromium demonstrates that color is not merely decorative. It is a window into how electrons move and interact within matter. Manganese quietly enables oxygen to exist in the atmosphere.
Oxygen feels like a permanent feature of Earth, but its presence depends on a delicate chain of processes. Manganese plays a crucial role in one of the most important of these. In photosynthetic organisms, clusters of manganese atoms help split water molecules, releasing oxygen as a byproduct. This reaction is extraordinarily demanding, requiring precise control over electrons and energy. Manganese's ability to shift between multiple oxidation states allows it to manage this process repeatedly without being consumed over immense spans of time. This mechanism filled the atmosphere with oxygen, transforming the planet's chemistry and making complex life possible. Without manganese acting as a catalytic scaffold, the buildup of oxygen would have been far slower or might not have occurred at all. Outside biology, manganese continues to influence oxygen chemistry in soils and minerals, affecting how oxygen moves through the environment.
The element's importance is easy to overlook because it rarely appears in large quantities. Yet it influences planetary in scale, quietly shaping the air itself. Iron defines the life cycle of stars and planets. Iron marks a turning point in cosmic history. Inside stars, nuclear fusion releases energy by combining lighter elements into heavier ones. This process continues until iron is formed. Beyond iron, fusion no longer yields energy, and the star's balance changes dramatically. For massive stars, the accumulation of iron can trigger collapse and explosion, scattering newly formed elements into space. In this way, iron acts as both a product and a limit. It ends one phase of stellar life and begins another. On planets, iron again takes on a defining role. Its density causes it to sink toward the center, forming cores that generate magnetic fields and influence tectonic activity. These fields can shield atmospheres and shape surface conditions. Iron's chemical behavior also makes it essential for life, enabling oxygen transport and energy conversion in living systems. Across scales, iron signals transitions. It tells stars when to die, planets how to organize themselves, and organisms how to function. Cobalt records magnetic history inside solid matter. Cobalt has a strong relationship with magnetism, one that allows it to preserve records of past conditions. When materials containing cobalt cool or solidify in the presence of magnetic fields, cobalt atoms can align in ways that lock in magnetic information. This property has been exploited in technologies that store data where tiny magnetic regions represent information. In natural settings, cobalt-bearing minerals can capture the direction and strength of ancient magnetic fields, offering clues about the past behavior of Earth's core and the movement of tectonic plates. Cobalt's magnetic sensitivity arises from the arrangement of its electrons, which produce strong magnetic moments. These moments interact with one another and with external fields in ways that are unusually stable. As a result, cobalt can act as a memory medium, preserving patterns long after the original field has vanished. This element transforms invisible forces into lasting physical traces, creating a bridge between what is fleeting and what endures. Nickel, in particular, helps reveal how planetary cores are formed. Closely bound to iron, it becomes part of the structural heart of many worlds. Together, these metals shape how planetary interiors melt, blend, and solidify under immense pressure, quietly determining the inner architecture of planets across the cosmos. In the early stages of planetary formation, dense materials sank inward, carrying nickel with them. The resulting iron-nickel mixtures behave differently than iron alone, affecting how heat flows and how magnetic fields are generated. By studying nickel-rich meteorites and deep Earth materials, scientists can reconstruct the processes that shaped planetary interiors billions of years ago. Nickel's resistance to corrosion also helps preserve these records, allowing ancient structures to survive largely unchanged. On Earth, nickel's role extends to the magnetic field that protects the surface from energetic particles. Without nickel contributing to core dynamics, planetary environments could be far less stable. Nickel's chemistry thus connects deep interior processes with surface habitability. Copper conducts more than just electricity through civilization. Copper's ability to carry electrical current is only one chapter in its long relationship with human societies. Long before modern technology, copper's malleability and resistance to corrosion made it one of the first metals humans could shape and reuse. It became part of tools, art, trade networks, and symbolic systems. Copper also conducts heat efficiently, influencing architecture, cooking, and energy transfer. In biology, copper plays essential roles in enzymes that manage electron flow, mirroring its technological uses on a microscopic scale. The element's distinctive color and antimicrobial properties have shaped cultural practices as well as practical ones. Copper coins, roofs, and vessels age visibly, recording environmental exposure over time. This patina becomes a kind of historical layer, marking the passage of years. Copper's conductivity is not limited to electrons. It carries information, tradition, and continuity across generations. Zinc fine-tunes biology at the molecular level. Zinc rarely builds large structures, but it excels at precision. In living systems, zinc atoms often sit at the center of proteins, stabilizing their shapes and enabling them to perform specific tasks. These proteins control gene expression, repair damaged molecules, and regulate chemical reactions with remarkable accuracy. Zinc's chemistry allows it to bind securely without undergoing unwanted reactions, making it an ideal structural assistant. A slight imbalance in zinc availability can disrupt numerous biological processes, underscoring how finely tuned its role is. Unlike elements that act through bulk properties, zinc works through placement and coordination. It influences systems not by force, but by fit. Beyond biology, zinc's protective qualities are harnessed in materials where it shields other metals from corrosion. This protective role echoes its biological function, guarding delicate processes from damage. Zinc demonstrates how small-scale interactions can have outsized effects when they are precisely orchestrated. Gallium melts in your hand because its atoms barely hold together. Gallium is a metal that quietly defies intuition. It looks solid, shiny, and stable at room conditions. Yet it melts at a temperature only slightly above the warmth of human skin. This strange behavior comes from how weakly gallium atoms bond to one another in their solid form. Unlike most metals, which pack their atoms into simple, repeating patterns, gallium forms an unusual structure where pairs of atoms cling tightly while neighboring pairs interact only loosely. The result is a solid that is already halfway to falling apart. When the small amount of heat is added, such as from your hand, those weak connections give way and the metal flows. This softness is not fragility in the everyday sense. Gallium is chemically resilient and does not easily corrode or react with air. Its odd melting behavior instead reveals how sensitive matter can be to suffer in atomic arrangement. Gallium reminds us that solidity is not guaranteed. Even metals can exist on the edge between order and motion, held together by bonds that barely agree to stay intact. Germanmanium helped reveal the quantum nature of solids. Germanmanium played a quiet but pivotal role in changing how humans understand materials. Before its electronic properties were explored, solids were often treated as simple collections of atoms, whose behavior could be averaged and smoothed out. Germanmanium challenged that view. When scientists began studying how electricity moved through germanmanium, they discovered that its behavior could not be explained without invoking quantum rules. Electrons in germanium occupy energy bands rather than roaming freely or staying fixed, and tiny changes in purity or structure can dramatically alter how current flows. This sensitivity made germanmanium one of the first materials used to demonstrate how quantum mechanics governs bulk matter, not just isolated particles. Early electronic components relied on germanmanium to amplify signals and switch currents, revealing that solids could be engineered by manipulating quantum states. Although other materials later became more practical, germanmanium's legacy remains foundational. It showed that the macroscopic world of devices and circuits is inseparable from the strange, probabilistic rules operating at the atomic scale. Arsenic blows the boundary between poison and medicine. Arsenic has long been associated with danger, secrecy, and death, and for good reason. Many arsenic compounds interfere with essential biological processes, disrupting how cells produce energy and maintain balance. Yet the same ability to interfere can be harnessed with precision. In carefully controlled forms and doses, arsenic-based compounds have been used to treat certain diseases, particularly where abnormal cells must be targeted without destroying surrounding tissue. This dual nature arises from arsenic's chemical similarity to elements that biology normally relies on. Cells sometimes mistake arsenic for something useful, allowing it to slip into critical pathways. Whether that intrusion causes harm or healing depends entirely on context and control. Arsenic therefore exposes some uncomfortable truth about chemistry and biology. The line between remedy and toxin is not drawn by the element itself, but by how it is used. On the periodic table, arsenic sits calmly among its neighbors. In life, it demands respect, reminding us that chemistry is powerful precisely because it can cut both ways. Selenium participates in life through trace precision. Selenium operates in biology at extremely small concentrations. Yet its impact is outsized. Within living cells, selenium is incorporated into specialized proteins that manage oxidative stress and help maintain chemical balance. These proteins protect cells from damage caused by reactive molecules that are constantly produced during normal metabolism. Selenium's effectiveness comes from its precise placement. A single chelenium atom within a protein can alter how electrons move, enabling reactions that would otherwise proceed too slowly or not at all. Too little chelenium and these protective systems falter. Too much and normal chemistry is disrupted. This narrow window highlights how finely tuned biological systems can be. Chelenium is not a bulk building material. It is a regulator, quietly adjusting reaction rates and maintaining stability. Its role illustrates a broader principle of life that survival often depends not on abundance, but on exactness. The periodic table includes many elements that matter only in trace amounts, and selenium stands as one of the clearest examples of how small presences can have decisive effects. Bromine remains liquid because of a delicate atomic balance. Bromine occupies a rare state among elements existing as a liquid under ordinary conditions, This unusual behavior arises from a balance between opposing tendencies. Bromine atoms attract one another more strongly than lighter gases do, which encourages condensation. At the same time, they do not pack together as tightly as solids typically require. The result is a substance that flows yet evaporates readily, hovering between order and escape. This physical state has important consequences for bromine's chemistry. As a liquid, bromine can spread, diffuse, and react in ways that gases and solids cannot. It becomes mobile without being invisible. In nature and industry, this mobility allows bromine to participate in reactions that shape materials, control microbial growth, and influence atmospheric chemistry. Bromines' liquid form is not an accident. It reflects how small changes in atomic mass and intermolecular attraction can dramatically alter how matter behaves. Bromine shows that phase is not just about temperature, but about subtle balances written into the atoms themselves. Krypton exists largely to remind us what inert really means. Krypton belongs to a family of elements that are famously unreactive. Yet Krypton's behavior adds nuance to that reputation. Its atoms have electron configurations that leave little incentive to bond, making Krypton largely indifferent to chemical surroundings. For a long time, this led scientists to assume Krypton was completely aloof. Later discoveries showed that under extreme conditions, even Krypton can be coaxed into forming compounds, though only reluctantly. This makes Krypton a benchmark. It defines what near-total chemical indifference looks like, while also revealing that no element is absolutely isolated from interaction. Krypton's presence in the atmosphere is steady and unchanging, making it useful for tracing physical processes without chemical interference. In lighting and detection technologies, Krypton's predictable behavior becomes an asset. It does not surprise. In a periodic table full of drama, Krypton offers a lesson in restraint, showing how stability and silence can be properties worth understanding in their own right. Rubidium responds dramatically to even tiny energy changes. Rubidium is an element that reacts not just strongly, but eagerly. Its outermost electron is held so loosely that even small inputs of energy can free it or shift its behavior. This remarkable sensitivity makes rubidium highly reactive, especially when it encounters substances that can easily stabilize its missing electron. Yet that very same quality also makes rubidium exceptionally valuable for precision measurement. Rubidium atoms can be guided and controlled with light and electromagnetic fields, allowing scientists to detect extraordinarily subtle shifts in energy with calm, elegant accuracy. This property has made rubidium valuable in experiments where timing, frequency, and stability must be controlled with exceptional accuracy. The element's behavior highlights a deep connection between reactivity and responsiveness. An atom that is easy to disturb chemically is also easy to probe physically. Rubidium, therefore, sits at an intersection between chemistry and measurement science. It shows how an element's willingness to give up an electron can translate into both dramatic reactions and delicate control, depending on how that willingness is engaged. Strontium leaves fingerprints in bones and stars alike. Strontium has a curious habit of following calcium wherever it goes. In living organisms, strontium can substitute for calcium in bones and teeth, becoming incorporated into hard tissues in trace amounts. This substitution leaves a chemical record that can reveal information about diet, environment, and movement. In astronomy, strontium also leaves recognizable signatures in the light emitted by stars. By analyzing these signatures, scientists can learn about stellar composition and the processes that built heavier elements over time. The fact that the same element can inform both archaeology and astrophysics is striking. It shows how atomic behavior remains consistent across vastly different settings. Strontium's chemistry allows it to fit into structures designed for calcium, yet its distinct identity makes it detectable afterward. This dual role turns strontium into a tracer, a quiet witness that marks where matter has been and what conditions it has experienced, whether in a skeleton or a distant star. It behaves like a chemical chameleon. It really rarely draws attention to itself. Yet it adapts easily to many chemical environments. It can form stable compounds with oxygen, integrate into crystalline lattices, and influence material properties without dominating them. This flexibility makes it useful in applications where subtle modification is needed rather than wholesale change. Its ions can adjust crystal structures, alter electronic behavior, and improve performance in optical and magnetic materials. Yttrium's adaptability comes from its size and charge, which allow it to fit into multiple chemical niches. It neither insists on one role nor resists transformation. Instead, it adjusts. This chameleon-like behavior makes it really difficult to categorize by simple rules, but extremely valuable in practice. It demonstrates that influence does not always require abundance or aggression. Sometimes an element shapes outcomes precisely because it blends in, modifying systems from within rather than imposing itself from without. Zirconium resists corrosion in some of the harshest environments known. Zirconium has an exceptional ability to endure conditions that would rapidly degrade most metals. When exposed to air or water, zirconium forms a thin oxide layer that adheres tightly to the surface and blocks further reaction. This layer does not flake or crack easily, allowing the metal beneath to remain protected even under high temperatures and intense chemical stress. This property makes zirconium invaluable in environments where failure is not an option, such as systems exposed to heat, pressure, and reactive substances simultaneously. Zirconium stability is not passive. It actively maintains its own protection through atomic rearrangement at the surface. This self-defense mechanism arises from zirconium's strong affinity for oxygen combined with the strength of the resulting oxide. The element shows how corrosion resistance is not simply about being unreactive, but about reacting in exactly the right way. Zirconium turns exposure into armor, using chemistry itself as a shield. Niobium allows electricity to flow without resistance under special conditions. Niobium becomes extraordinary when cooled and prepared in very specific ways. Under these conditions, it can enter a state where electrical current passes through it without losing energy as heat. This phenomenon is not just improved conductivity, but a complete absence of resistance. Electrons move in coordinated pairs, flowing as if the material itself has stepped out of the way. What makes niobium especially important is that this behavior occurs at temperatures that are achievable with modern cooling techniques, unlike many other materials that require far more extreme conditions. Because of this, niobium is used in powerful magnets that bend particle beams, guide medical imaging, and probe the structure of matter itself. Inside these systems, enormous currents circulate endlessly without fading. Niobium shows that electricity does not always have to fight its way through matter. Under the right circumstances, matter can cooperate completely, revealing a hidden mode of behavior that feels almost frictionless in both a physical and conceptual sense. Molybdenum strengthens structures at temperatures that would destroy most metals. Molybdenum excels where heat becomes a destructive force.
As temperatures rise, many metals soften, creep, or fail outright as atomic vibrations disrupt their structure. Molybdenum resists this breakdown. Its atoms bond strongly, maintaining rigidity and strength even when glowing hot.
This resilience makes molybdenum essential in environments where intense heat is unavoidable, such as high-temperature engines and industrial furnaces. When added in small amounts to steel, molybdenum dramatically improves resistance to deformation and fracture, extending the lifespan of critical components. What makes this particularly fascinating is that molybdenum does not simply endure heat. It actively alters how materials respond to it, redistributing stress and slowing the movement of defects through the atomic lattice. In this way, molybdenum acts as a guardian against thermal chaos. It preserves order where energy would otherwise unravel structure, demonstrating how a single element can redefine the limits of endurance. Technetium was the first element created entirely by human effort. It holds a singular place in scientific history, not uncovered through mining or refinement, but brought into being through intentional creation. Because no stable form of technetium exists, any that may have formed naturally in the distant past has long since faded away, leaving only traces made by human hands. When scientists finally produced technetium, they did so by inducing nuclear reactions that transformed other elements into something entirely new. This achievement proved that the periodic table was not only a catalog of what nature provided, but a framework that could be extended by human ingenuity. Technetium's existence confirmed theoretical predictions and demonstrated that elements could be engineered rather than found. Today, technetium plays an important role in medical imaging, where its radioactive properties are used to trace biological processes inside the body. Its atoms decay in ways that can be detected externally, offering insight without invasive procedures. Technetium stands as a symbol of a turning point when humans moved from observers of matter to participants in its creation. Ruthenium improves reactions by offering surfaces at the atomic scale. Ruthenium is rarely noticed by name, yet it plays a powerful role wherever reactions must be guided rather than forced. Its atoms provide surfaces that encourage molecules to assemble, break apart, or rearrange more efficiently. These surfaces act like carefully shaped landscapes, lowering energy barriers and allowing reactions to proceed along gentler paths. What makes ruthenium special is its balance. It binds reactants strongly enough to influence them, but not so strongly that they become trapped. This balance allows reactions to repeat over and over without consuming the metal itself. In many chemical systems, ruthenium acts as a quiet facilitator, increasing efficiency while remaining unchanged. This catalytic behavior reflects a deeper truth about chemistry. The control often comes from subtle interactions rather than brute force. Ruthenium demonstrates how the right atomic surface can shape outcomes invisibly, guiding matter through transformations that would otherwise be slow, wasteful, or impossible. Rhodium reflects light with unusual efficiency. Rhodium has an exceptional ability to reflect light, especially in environments where heat and chemical stress would dull other metals. This reflective power arises from how rhodium's electrons respond to incoming light, rebounding energy rather than absorbing it. As a result, rhodium surfaces maintain brightness and clarity even under demanding conditions. This makes rhodium valuable in optical systems and high-performance coatings where precision matters. Beyond reflection, rhodium also resists corrosion, allowing its reflective qualities to persist over time. The element's durability ensures that light interacting with rhodium behaves predictably without being scattered by surface degradation. In this way, rhodium controls not just chemistry, but perception. It manages how energy is returned to the environment. Rhodium shows that light itself can be engineered through atomic choice, and that reflection is not merely about shininess, but about stability, structure, and electronic response working together.
Palladium absorbs hydrogen in unexpected ways. Palladium has a remarkable ability to take hydrogen atoms into its own structure. Rather than merely coating the surface, hydrogen can diffuse into the metal, occupying spaces between palladium atoms. This process happens reversibly, allowing hydrogen to enter and leave without destroying the metal's integrity. The behavior challenges simple ideas about solids as rigid and impenetrable. Palladium behaves more like a flexible host, accommodating hydrogen within its lattice. This property has made palladium invaluable for studying hydrogen behavior and for developing technologies related to energy storage and purification.
What is especially intriguing is that palladium can absorb large amounts of hydrogen vital to its own volume, altering its physical properties in the process. The metal expands slightly, and its electrical characteristics change. Palladium reveals that metals are not closed systems. They can interact with the smallest atoms in ways that blur the line between solid and solution. Silver balances beauty with unmatched conductivity. Silver has long been admired for its visual appeal, but its true distinction lies in how effortlessly it allows electrons to move. Among all elements, silver offers the least resistance to electrical flow. This exceptional conductivity arises from the freedom of its outer electrons, which glide through the metal with minimal scattering. As a result, silver is used wherever signals must be transmitted cleanly and efficiently. At the same time, silver's surface interacts with light in ways that create a distinctive luster, making it equally valued for ornamentation. Beyond aesthetics and electronics, silver also influences chemistry and biology through its interactions with microorganisms. Its ions can disrupt essential processes in cells, lending silver antimicrobial properties. This combination of efficiency, beauty, and biological impact makes silver unusually multifaceted. It is an element that appeals to both engineers and artists, showing that function and form can emerge from the same atomic traits. Cadmium reveals how toxic elements interfere with life. Cadmium offers a stark lesson in how chemistry can undermine biology. Its atoms resemble those of essential elements closely enough that living systems sometimes absorb cadmium by mistake. Once inside, cadmium interferes with enzymes and cellular machinery, disrupting normal function. Unlike nutrients that are carefully regulated, cadmium accumulates, compounding its effects over time. This persistence makes it particularly dangerous even at low exposure levels. Studying cadmium has helped scientists understand how toxic elements exploit biological pathways, revealing vulnerabilities in cellular systems. Cadmium's behavior shows that toxicity often arises not from dramatic reactions, but from subtle interference. It blocks, displaces, and distorts processes that normally run smoothly. Through cadmium, researchers have learned more about metal regulation, detoxification, and the fine balance that sustains life. The element serves as a reminder that biological compatibility depends on precise chemical fit, and that small deviations can have serious consequences. Indium bends rather than breaks at the atomic level. Indium is unusual among metals because it deforms easily without fracturing. When pressure is applied, indium atoms slide past one another smoothly, allowing the metal to bend and flow rather than crack. This softness arises from weak bonding between atomic layers, which can rearrange without accumulating stress. As a result, indium can form tight seals and conform to irregular surfaces, maintaining contact where more rigid materials would fail. This property is invaluable in applications that require reliable connections under changing conditions,
Indium's flexibility also reveals how atomic arrangement governs macroscopic behavior. A metal's hardness or softness is not an intrinsic mystery, but the outcome of how atoms share and distribute electrons. Indium teaches that strength is not the only desirable trait. Sometimes resilience comes from yielding gracefully, absorbing stress by adapting rather than resisting. Tin helped shape human history long before modern science.
Tin played a decisive role in early technological development by combining with copper to form bronze. This alloy was harder and more durable than either metal alone, allowing tools, weapons, and structures to reach new levels of effectiveness. The availability of tin influenced trade routes, cultural exchange, and the rise of civilizations. Entire regions gained prominence because they could supply this crucial ingredient. Tin's importance lay not in abundance, but in transformation. A small amount could dramatically change the properties of another metal. This leverage made tin strategically significant long before its atomic nature was understood. Even today, tin continues to influence materials through coatings and alloys that protect against corrosion and improve performance. Tin's story shows how elemental properties can ripple outward into social and historical change. The periodic table is not only a scientific framework, it is also a quiet driver of human history. Antimony sits at the boundary between metals and non-metals. Antimony occupies a curious middle ground where familiar categories begin to blur. It can conduct electricity, yet not nearly as freely as true metals. It can form brittle solids that shatter rather than bend, a trait more often associated with non-metals. This mixed behavior comes from how antimetallic electrons are arranged and how strongly they bind to one another. In some contexts, antimony behaves like a metal that has lost confidence. In others, like a non-metal that almost fits in. This ambiguity makes antimony especially valuable in fine-tuning materials. Small amounts can dramatically change hardness, conductivity, and stability, particularly in alloys where balance matters more than extremes. Antimony has also played a role in shaping type metals, flame retardants, and electronic components where its borderline nature becomes an advantage. Rather than committing fully to one identity, antimony adapts on the periodic table. It marks a transition zone where simple labels stop working, reminding us that matter often lives in gradients rather than categories. Tellurium is rarer than gold in Earth's crust. Gold is famous for its rarity, yet toom is even more scarce. Its atoms are scattered thinly through Earth's crust, rarely concentrating into rich deposits. This scarcity is not due to instability, but to how it behaves chemically. It tends to bond with other elements in ways that prevent it from accumulating on its own. As a result, thorium is often found as a trace component within other minerals, rather than as a primary resource. Despite its rarity, thorium plays an outsized role in modern technology. Its electronic properties make it valuable in specialized materials where precise control of conductivity is required. Thorium also forms compounds that respond sensitively to heat and light, opening pathways for energy conversion and detection. The contrast between its low abundance and high utility is striking. Thorium shows that importance is not a function of quantity. Sometimes the rarest ingredients are the ones that enable the most delicate and powerful effects. Iodine governs the speed of thought through chemistry. Iodine plays a quiet but profound role in how quickly minds and bodies function. It is a key component of hormones that regulate metabolism, the process that determines how fast cells convert energy and carry out chemical reactions. When iodine levels are balanced, these hormones help set a steady rhythm for growth, temperature regulation, and neural activity. When iodine is scarce or excessive, that rhythm can slow or race, affecting everything from physical development to cognitive performance. What makes iodine fascinating is how such a small amount can have such sweeping influence. It does not build tissues or transmit signals directly. Rather than acting in sudden bursts, it subtly adjusts the pace at which countless processes unfold. Iodine's chemistry allows it to bind in ways that stabilize hormone structures, while still permitting fine, precise control over their activity. In this role, iodine becomes a kind of molecular timekeeper, quietly setting the rhythm of life's internal processes. On the periodic table, it appears as a halogen, known for its distinctive and carefully balanced reactivity. In living systems, it quietly helps decide how fast life itself proceeds. Xenon forms compounds that once seemed impossible. For a long time, xenon was thought to be entirely inert, an element that would not engage in chemistry under any circumstances. Its electrons appeared perfectly content, leaving no obvious openings for bonding. This assumption made xenon a benchmark for chemical inactivity. That view changed when scientists discovered that xenon could, under the right conditions, form stable compounds. These compounds required highly reactive partners and carefully controlled environments, but once formed, they were unmistakable. The discovery forced a rethinking of what chemical inertness truly means. Xenon had not changed. Human understanding had. Its electrons could be persuaded into sharing under sufficient pressure and influence. Xenon's compounds are rare and specialized, but they demonstrate that the periodic table still holds surprises. Even elements long assumed to be silent participants can reveal hidden complexity. Xenon teaches that chemical rules are not absolutes, but tendencies that can be stretched under the right circumstances. Cesium defines time itself through atomic motion. Cesium plays a role that reaches beyond chemistry into the fabric of daily life. Its atoms oscillate between energy states at an extraordinarily regular rate when exposed to specific radiation. This consistency is so reliable that it has been chosen as the basis for defining the second. Time, as used in science, navigation, and communication, is anchored to the behavior of cesium atoms. What makes this remarkable is that an abstract concept like timekeeping rests on the predictable motion of electrons within a single element. Cesium's suitability for this role comes from how easily its outer electron responds to energy, producing transitions that are both sharp and stable. These atomic rhythms do not drift with temperature or pressure in the way mechanical systems do. As a result, cesium provides a universal reference that can be reproduced anywhere. The periodic table thus contains not just substances, but standards. CEM shows that matter can be used to measure ideas as intangible as time itself. Barium reveals hidden structures inside the human body. Barium has a unique ability to make the invisible visible. Certain barium compounds interact strongly with radiation used in medical imaging, absorbing it in ways that create clear contrast. When introduced into the body in controlled forms, barium outlines internal structures that would otherwise blend into the background. This allows physicians to observe movement, shape, and function without surgery. The effectiveness of barium comes from its dense atomic structure, which interacts readily with penetrating radiation. At the same time, its chemistry can be managed so that it passes through the body without being absorbed into tissues.
This careful balance between visibility and containment makes barium an invaluable diagnostic tool. Beyond medicine, barium also appears in minerals and industrial materials where its properties influence weight and stability.
Barium demonstrates how atomic characteristics can be harnessed to reveal hidden worlds, turning internal processes into readable signals. Lanthanum begins a family of elements with nearly identical behavior. Lanthanum marks the start of a remarkable group known for their similarity. The elements that follow share closely related chemical properties, making them difficult to separate and study individually. This near sameness arises because the electrons that define their chemistry occupy similar arrangements, shielding deeper differences from most reactions. As a result, these elements often appear together in nature and behave as a collective rather than as distinct personalities. Lanthanum's position at the front of this family makes it a reference point, setting the tone for what follows. Studying lanthanum helps scientists understand the subtle variations that emerge across the group, revealing how small changes in atomic structure can accumulate into meaningful differences. These elements are crucial in modern technologies that rely on precise control of magnetic, optical, and electronic behavior. Lanthanum introduces a region of the periodic table where individuality is muted and nuance becomes the main story. Cerium switches oxidation states with remarkable ease. Cerium stands out for how readily it changes its electronic identity. It can lose different numbers of electrons depending on its environment, allowing it to shift between chemical states with little resistance. This flexibility makes cerium exceptionally useful in reactions where electrons must be transferred smoothly. Cerium compounds can store and release oxygen, participate in redox cycles, and buffer chemical systems against sudden changes. This ability to adapt gives cerium a role as a mediator, smoothing transitions that might otherwise be abrupt or inefficient. In materials, cerium's shifting states help control color, reactivity, and stability. In environmental contexts, cerium compounds assist in managing pollutants by facilitating controlled reactions. Cerium's behavior highlights an important theme of the periodic table. Some elements are valuable not because they are fixed, but because they are fluid. Cerium thrives in change, using flexibility as its defining strength. Cadmium manipulates light in subtle ways. Cadmium interacts with light in ways that are delicate rather than dramatic. Its atoms absorb and emit specific wavelengths, allowing it to fine-tune color and transparency in materials. When incorporated into glasses and crystals, cadmium can filter light selectively, enhancing contrast or producing gentle hues that shift with illumination. These effects arise from electronic transitions that are highly sensitive to their surroundings. Small changes in structure or composition can alter how cadmium responds to light. This sensitivity makes it valuable in optical applications, where precision matters more than brightness. Praseomium's influence is often invisible until conditions are just right, at which point its presence becomes unmistakable. It demonstrates that control over light does not always require intensity. Sometimes it comes from quiet adjustments at the atomic level, shaping perception through restraint rather than force. Neodymium creates magnets strong enough to reshape technology. Neodymium has transformed how humans harness magnetism. When combined with specific partners, neodymium forms magnets that are extraordinarily strong for their size. This strength arises from how neodymium's electrons align and reinforce magnetic fields within a solid structure. The resulting magnets are compact yet powerful, enabling miniaturization across countless technologies. Devices that once required large, heavy components can now be smaller, lighter, and more efficient.
Neodymium magnets appear in motors, generators, and precision instruments where reliable magnetic force is essential. Their impact extends beyond convenience. By improving efficiency and reducing material requirements, these magnets influence energy use and design possibilities. Neodymium shows how an element's internal electronic arrangement can ripple outward into technological change, reshaping what engineers consider practical or possible. Promethium exists only briefly in nature. Promethium occupies a strange place among the elements because it does not truly belong to the long-lived world around us. Any promethium that may have existed when Earth formed has long since decayed into other elements. What little promethium appears today is generated fleetingly through radioactive processes, emerging for a short time before transforming again. This makes promethium an element defined by impermanence. Its atoms are real, measurable, and chemically distinct, yet they refuse to linger. Studying promethium requires catching it in the act of becoming something else. This fleeting existence reveals how the periodic table includes not just stable matter, but transitional matter as well. Promethium shows that elements can function more like events than substances. They are moments in a chain rather than destinations. In laboratories, promethium can be produced deliberately, allowing scientists to explore its properties despite its instability. Its behavior helps illuminate how radioactive decay reshapes matter over time. Promethium reminds us that not everything in the universe is meant to endure. Some things exist only to pass through, leaving traces that help us understand the deeper rules governing change. Samarium helps convert heat directly into electricity. Samarium plays a role in a remarkable process where temperature differences can be transformed directly into electrical energy. Certain samarium-based materials allow electrons to move in response to heat flow, generating usable current without moving parts. This phenomenon relies on precise electronic structures that respond predictably to thermal energy. Samarium's electrons occupy states that make this conversion efficient under the right conditions. The result is a quiet form of power generation that does not rely on combustion or rotation. Instead, it draws energy from gradients, turning waste heat into something useful. Samarium also finds a place in magnetic materials, where stability across a wide range of temperatures is essential. Its atomic structure helps these materials retain their performance even as conditions shift and fluctuate. This balance between thermal resilience and magnetic strength makes samarium a quietly versatile contributor to advanced technologies. It shows how elements can connect different forms of energy linking heat and electricity through elegant atomic design rather than mechanical complexity. Europium produces some of the purest reds and blues known. Europium has a special talent for interacting with light in vivid and precise ways. When incorporated into certain materials, europium emits light at very specific wavelengths, producing deep reds and clear blues that are difficult to achieve otherwise. This precision arises from how europium's electrons shift between energy levels that are well isolated from their surroundings. Because these transitions are so sharply defined, the colors remain stable and saturated. Europium's light emission has been essential in creating displays and lighting systems where color accuracy matters. Beyond technology, europium's behavior illustrates how atomic structure governs perception. A tiny change in electron arrangement can determine whether light appears warm, cool, or neutral. Europium demonstrates that color is not subjective at its core. It is a physical outcome,
shaped by electrons responding to energy with remarkable consistency. Gadolinium reacts intensely to magnetic fields. Gadolinium stands out for how strongly it responds to magnetism. Its atoms possess unpaired electrons that align readily with external magnetic fields, producing pronounced effects. This responsiveness makes gadolinium valuable wherever magnetic sensitivity is required. In certain applications, gadolinium compounds change temperature when exposed to changing magnetic fields, revealing a direct link between magnetism and heat. This behavior has been explored for cooling technologies that operate without traditional refrigerants. Gadolinium's magnetic properties also make it useful in enhancing contrast in imaging techniques, where its presence alters magnetic environments in detectable ways. The element's behavior highlights how magnetism emerges from electron arrangement rather than bulk size. Gadolinium shows that even subtle shifts in electronic structure can produce dramatic macroscopic effects. It turns invisible magnetic forces into measurable changes, offering a bridge between abstract fields and tangible outcomes. Terbium alters materials through minute concentrations. Terbium exerts influence far beyond what its small quantities would suggest. When added in tiny amounts to certain materials, terbium can significantly change how they respond to light, magnetism, or mechanical stress. This outsized effect comes from how terbium's electrons interact with their surroundings, introducing new energy pathways without overwhelming the host structure. Because of this, terbium is often used not as a main ingredient, but as a modifier. It fine-tunes performance rather than defining it outright. In magnetic materials, terbium can enhance sensitivity or stability. In optical systems, it can adjust color and response time. Terbium's role emphasizes a recurring theme in the periodic table that impact is not always proportional to presence. Sometimes the smallest additions produce the most meaningful shifts. Dysprosium resists demagnetization better than almost any element. Dysprosium possesses a remarkable ability to hold on to magnetic alignment even under conditions that would weaken other materials. This resistance to demagnetization arises from strong interactions between dysprosium's electrons, which create internal forces that oppose disruption. When incorporated into magnetic systems, dysprosium helps preserve performance at elevated temperatures or under mechanical stress. This stability is crucial in technologies where magnets must operate reliably over long periods and in challenging environments. Dysprosium's contribution is often invisible to users, yet without it, many high-performance systems would lose effectiveness. The element illustrates how durability in physical properties depends on atomic scale interactions. Dysprosium does not create magnetism from scratch. It protects it, reinforcing order against the constant tendency toward disorder. Homium generates the strongest magnetic moments of all elements. Homium holds a distinction rooted in the behavior of its electrons. Its atoms produce exceptionally strong magnetic moments, meaning each atom contributes a powerful magnetic influence. This arises from the number and arrangement of unpaired electrons that align coherently. As a result, homium responds dramatically to magnetic fields and can enhance magnetic effects when incorporated into materials. This strength makes homium useful in specialized applications, where intense magnetic responses are required within compact spaces. Hom's behavior also offers insight into how magnetism scales. It shows that atomic properties can be amplified collectively, turning microscopic alignment into macroscopic force. Homium reveals magnetism at its most concentrated, demonstrating the upper limits of how strongly matter can respond to magnetic influence. Herbium quietly amplifies light across the planet. Herbium plays a hidden but essential role in modern communication. When light passes through materials containing herbium, it can be amplified without converting the signal into another form. This amplification occurs because herbium's electrons absorb energy and remit it as light of the same wavelength. The process preserves information while boosting signal strength. This property allows light to travel vast distances through optical systems without fading. Herbium does its work silently, embedded within fibers that carry voices, data, and images across continents and oceans. The element's ability to strengthen light without distortion highlights the precision of atomic interactions. Herbium shows how subtle electronic behavior can underpin global connectivity, turning fragile photons into reliable messengers. Thium is one of the rarest stable elements on Earth. Thulium exists in Earth's crust only in minute amounts, dispersed thinly among other materials. It rarely forms concentrated deposits, making it difficult to isolate in significant quantities. Despite this scarcity, thulium remains stable, quietly persisting rather than decaying away. Its rarity is a matter of distribution rather than instability. Thium's atoms fit into minerals without drawing attention, blending into complex chemical environments. This makes thium challenging to study, but also intriguing. When isolated, it exhibits properties that are useful in precise applications involving light and radiation. Thium illustrates how rarity does not imply insignificance. Even elements that are barely present can reveal unique behaviors once they are finally brought into focus. Yttrium behaves differently under pressure and light. Yttrium displays a flexibility but sets it apart from many of its neighbors. Under ordinary conditions, it behaves in one way, but when exposed to pressure or light, its electronic structure can shift noticeably. These shifts alter how it conducts electricity, absorbs energy, and interacts with other atoms. This responsiveness makes it a valuable probe for studying how matter changes under extreme conditions. By observing how it reacts, scientists gain insight into the interplay between electrons and their environment. Yttrium's behavior challenges the idea that an element has a single, fixed personality. Instead, it shows that context matters deeply. The same atom can express different traits depending on the forces acting upon it, revealing the adaptable nature of matter itself. Yttrium closes the lanthanide series with exceptional density. Yttrium marks the quiet conclusion of a long family of elements that often behave as a collective. Unlike many of its relatives, lutetium stands out for its compactness. Its atoms pack together more tightly than any other lanthanide, giving it an unusually high density for its size. This density reflects how strongly its electrons are bound and how efficiently its nucleus pulls surrounding charge inward. Yttrium's compact nature makes it behave more like elements that come after the lanthanides, acting as a bridge between two regions of the periodic table. Chemically, it is often more predictable than its neighbors, which makes it useful as a reference point when studying subtle trends across the series. Lutetium's rarity and cost limit its everyday use, but its precision matters deeply in scientific contexts where small differences carry large meaning. It closes a chapter, not with drama, but with clarity, offering a final, tightly bound expression of a complex elemental family. Hafnia absorbs neutrons with extreme efficiency. Hafnium has a remarkable appetite for neutrons, particles that normally pass unnoticed through most materials. When neutrons encounter hafnium nuclei, they are readily captured, altering nuclear behavior in powerful ways. This property makes hafnium uniquely valuable in environments where controlling nuclear reactions is essential. By absorbing neutrons, hafnium can slow or regulate processes that would otherwise accelerate uncontrollably. What makes this even more striking is that hafnium achieves this without undergoing rapid decay or structural damage. Its nuclei remain stable even as they intercept particles with significant energy. Hafnium's effectiveness comes from the detailed structure of its nucleus, which presents favorable conditions for neutron capture. This behavior reveals how the periodic table encodes not only chemistry, but nuclear interaction as well. Hafni shows that some elements exert influence at depths far beyond electrons and bonds, reaching into the heart of the atom itself. Tantalum remains stable in environments that dissolve most metals. Tantalum is defined by its refusal to react. When exposed to acids, heat, or corrosive conditions that would rapidly degrade other metals, tantalum holds its ground. This stability arises from a dense oxide layer that forms instantly on its surface and clings tightly, sealing the metal beneath from further attack. Unlike fragile coatings that peel away, tantalum's protective layer becomes part of its identity. This resilience allows tantalum to survive in chemical environments where failure is otherwise inevitable. Beyond resistance, tantalum also maintains strength and structural integrity under stress, making it reliable where both chemical and mechanical challenges coexist. Its name has become associated with endurance for good reason. Tantalum demonstrates that reactivity is not the only path to importance. Sometimes, an element's greatest contribution is its ability to remain unchanged, preserving function and form when everything around it is trying to break it down. Tungsten survives temperatures that rival stellar surfaces. Tungsten possesses one of the highest melting points of all elements, allowing it to remain solid at temperatures that would reduce most metals to liquid or vapor. This extraordinary endurance comes from the strength of the bonds between tungsten atoms, which resist the violent vibrations induced by heat. Tungsten does not merely tolerate high temperatures. It maintains shape and strength when glowing intensely. This property has made tungsten indispensable in environments where heat is unavoidable and failure is not an option. At the atomic level, tungsten's electrons form bonds that are both numerous and strong, distributing energy without letting the structure collapse. Its presence reveals a fundamental truth about matter, that thermal resistance is not about mass alone, but about how atoms share electrons under stress. Tungsten stands as a reminder that even under conditions approaching those found in stars, some forms of matter can endure. Rhenium resists wear through extraordinary atomic bonding. Rhenium is one of the least reactive and most wear-resistant elements known. Its atoms form bonds that are exceptionally strong and stable, resisting both mechanical abrasion and chemical attack. When incorporated into alloys, rhenium dramatically improves resistance to creep and fatigue, especially under extreme conditions. This resilience allows materials to maintain performance over long periods of stress, heat, and pressure. Rhenium's effectiveness stems from how its electrons contribute to bonding networks that are difficult to disrupt. These networks distribute forces evenly, preventing weak points from forming. Although rhenium is rare and expensive, its impact is profound wherever reliability matters more than cost. Rhenium illustrates how durability can be engineered at the atomic level, turning strong bonds into longilived performance. Osmium packs more mass into space than almost any other element. Osmium is astonishingly dense, compressing an enormous amount of mass into a small volume. Its atoms are remarkably heavy, packing together with extraordinary efficiency and leaving very little empty space between them. This extreme density comes from osmium's massive nucleus, combined with strong metallic bonds that draw its atoms tightly together. Holding osmium can feel like holding matter in its most concentrated form, as if weight itself has been gently intensified. Beyond its physical heft, osmium's density reflects the extremes of atomic structure. It shows how far matter can be compressed without collapsing into something fundamentally different. Osmium's rarity and brittleness limit its practical use, but its existence challenges intuition. It demonstrates that solid matter can approach limits where mass and space are nearly inseparable, revealing how compact the building blocks of the universe can become. The idiom marks catastrophic events in planetary history. Iridium is rare in Earth's crust, but relatively more common in certain cosmic materials. This contrast makes it a powerful marker of extraordinary events. When large extraterrestrial bodies collide with planets, they can deliver iridium-rich material to the surface. Layers enriched with iridium, therefore, act as signatures of impacts that reshaped environments on a global scale. These thin layers preserve evidence of sudden change, linking chemistry to deep time. Iridium's resistance to corrosion and alteration allows it to persist long after surrounding materials have transformed. This durability turns iridium into a geological memory, recording moments when planetary history took abrupt turns. Through iridium, scientists can read the aftermath of ancient catastrophes, connecting elemental distribution to events that altered the course of life and landscapes alike. Platinum catalyzes reactions without being consumed. Platinum excels at guiding chemical reactions while remaining unchanged itself. Its surface provides sites where molecules can gather, rearrange, and react more efficiently. Platinum binds reactants just strongly enough to weaken their internal bonds, lowering the energy needed for transformation. Once the reaction is complete, the products detach, leaving the platinum ready to assist again. This repeatable role makes platinum a cornerstone of catalysis. Its effectiveness depends on the precise arrangement of electrons at its surface, which creates a landscape suited for interaction without entrament. Platinum's resistance to corrosion ensures that it continues performing this role over long periods. The element embodies a subtle kind of power. It does not force change, but enables it, acting as a silent partner in countless chemical processes. Gold resists corrosion because of relativistic effects. Gold's famous resistance to tarnish is not just a chemical curiosity. It arises in part from effects rooted in the behavior of electrons moving at significant fractions of light speed near the nucleus. In gold atoms, these relativistic effects alter how electrons occupy orbitals, stabilizing bonds and reducing gold's tendency to react. This makes gold unusually noble, remaining unchanged in environments that corrode other metals. The same electronic shifts also influence gold's color, giving it a warm hue, unlike that of most metals. Gold's behavior reveals that even everyday materials can be shaped by principles usually associated with extreme physics. The periodic table quietly incorporates relativity into matter you can hold, and gold is one of the clearest examples of how deep physical laws surface in familiar substances. Mercury remains liquid through weak metallic bonding. Mercury defies expectations by remaining liquid at temperatures where other metals are solid. This unusual state arises from weak bonding between mercury atoms, which do not lock into a rigid lattice. The electrons that normally glue metal atoms together are less effective in mercury, allowing atoms to slide past one another easily. This fluidity gives mercury properties that are both useful and hazardous. It flows smoothly, forms reflective surfaces, and responds quickly to changes in temperature. At the same time, its mobility allows it to spread and interact with biological systems in harmful ways. Mercury's liquid nature shows that metallic bonding is not a single, fixed phenomenon. It can vary dramatically depending on atomic structure. Mercury stands as a reminder that even metals can blur the line between solid and fluid when their electrons refuse to cooperate fully. Thallium disrupts biology by mimicking essential elements. Thallium is dangerous not because it is violently reactive, but because it is deceptively convincing. Its atoms closely resemble those of elements that living systems depend on, particularly in size and charge. As a result, biological machinery can mistake thallium for something useful and allow it to enter cells through normal pathways. Once inside, thallium interferes with processes that rely on precise ionic balance. It disrupts how enzymes function, how nerves transmit signals, and how cells manage energy. Unlike nutrients, thallium offers no benefit once incorporated. It occupies critical sites and blocks proper chemistry from occurring. What makes this especially insidious is that the body has few immediate defenses against such impersonation. Thallium's effects accumulate quietly, revealing how biological systems are optimized for cooperation, not deception. Studying thallium has helped scientists understand how cells distinguish between similar elements and why that distinction sometimes fails. Thallium demonstrates that toxicity often arises not from force, but from imitation, exploiting the trust built into life's chemistry. Lead records human history in its isotopes. Lead carries within it a layered record of human activity stretching back thousands of years. Different sources of lead possess distinct isotopic signatures, subtle variations that act like fingerprints. When lead enters the environment through mining, construction, or manufacturing, it leaves behind a traceable mark. These marks can be found preserved in ice, sediments, and even human remains. By analyzing these isotopic patterns, scientists can reconstruct timelines of industrial activity, trade routes, and technological change. Lead thus becomes a historical archive written into the planet itself. Its persistence makes this possible. Once released, lead does not vanish easily. It accumulates and remains detectable long after its original use has ended. This durability has made lead both a hazard and a historian. It reminds us that material choices echo through time, leaving chemical evidence long after memories fade. The periodic table includes elements that not only shape history, but quietly remember it. Bismuth forms crystals that seem to defy geometry. Bismuth crystals captivate attention with their intricate stepped shapes that resemble impossible staircases. These forms emerge naturally as bismuth solidifies, growing layer by layer in patterns dictated by atomic arrangement. The geometry reflects how bismuth atoms prefer to bond and stack, creating repeating angles that produce symmetrical yet surreal structures. The vivid colors often seen on bismuth crystals come from thin surface layers that interfere with light, adding another dimension to their appearance. What makes these crystals especially fascinating is that their beauty arises from simplicity. There is no guiding hand, only atoms following local rules. Bismuth's crystal growth reveals how complex forms can emerge spontaneously from basic interactions. Beyond aesthetics, bismuth is also notable for its low toxicity compared to neighboring heavy elements. This combination of visual elegance and relative safety makes bismuth an outlier in its region of the periodic table, standing out as both gentle and strange. Polonium releases enormous energy from tiny amounts of matter. Polonium is defined by intensity. Even minute quantities release significant energy as their atoms decay. This energy does not come from chemical bonds, but from changes within the nucleus itself. When a polonium atom transforms, it emits particles that carry substantial energy relative to the atom's size. This makes polonium extraordinarily potent despite its scarcity. Its behavior illustrates the dramatic difference between chemical and nuclear processes. Rearranging electrons releases modest energy. Rearranging nuclei releases far more. Polonium's energy output also makes it dangerous, requiring careful handling and shielding. Yet, it has been studied for how efficiently it converts mass into energy on a small scale. Polonium reminds us that the periodic table includes elements whose significance lies not in quantity, but in concentration of effect. A few atoms can matter enormously when nuclear forces are involved. 18 is so rare that it barely exists at all. 18 is the rarest naturally occurring element in Earth's crust. At any given moment, only a tiny number of 18 atoms are present, formed briefly through radioactive decay and disappearing just as quickly. There is never enough 18 in one place to see, touch, or collect in a conventional sense. Its existence must be inferred from the particles it emits and the transformations it understarts. This makes a team more like a transient phenomenon than a material substance. Chemically, 18 is predicted to share traits with other halogens. Yet its extreme rarity makes direct study challenge you. Every observation is indirect, reconstructed from fleeting signals. 18's near absence highlights the limits of material existence. The periodic table includes not only what is abundant and stable, but also what is barely allowed to appear. Astatine occupies a space between presence and disappearance, testing the very idea of what it means for an element to exist. Radon seeps invisibly from the ground as a radioactive gas. Radon is produced deep within Earth as heavier elements slowly decay. Being a gas, radon can escape from rock and soil, drifting upward through cracks and pores. It has no color, smell, or taste, making its presence impossible to detect without instruments. Once released, radon continues to decay, emitting radiation that can interact with living tissue. This invisible journey from solid rock to open air reveals how nuclear processes can influence environments far from their origin. Radon's behavior also illustrates how elements change form as they move through decay chains, transforming from solid to gas while retaining their energetic character. Studying radon has improved understanding of geological processes, building safety, and radiation exposure. Radon reminds us that Earth is not chemically static. Even seemingly inert ground is an active source of transformation, quietly releasing matter shaped by nuclear history. Francium may be the most unstable, naturally occurring element. Francium sits at the extreme edge of stability among elements that appear naturally. Its atoms form through radioactive decay and vanish quickly, transforming into other elements almost as soon as they exist. Francium's instability makes it extraordinarily rare, with only a few atoms present at any given time. This fleeting nature makes direct study difficult, requiring sophisticated techniques to capture and observe individual atoms. Francium's behavior reflects the growing imbalance between forces inside very large nuclei. As size increases, stability becomes harder to maintain. Francium shows how the periodic table tapers into transience, where existence becomes a moment
rather than a state.
Its rarity is not due to scarcity of ingredients, but to the difficulty of holding such a nucleus together. Francium stands as a natural limit, marking how far ordinary matter can stretch before it unravels. Radium glows because its atoms fall apart. Radium emits a faint glow as a consequence of its own decay. As radium atoms break down, they release energetic particles that excite surrounding materials, causing light to be emitted. This glow is not a sign of vitality, but of transformation. Radium is constantly changing into other elements, releasing energy in the process. Its discovery revealed that atoms are not immutable, but can spontaneously alter their identity. This realization reshaped understanding of matter and energy. Radium's glow fascinated early observers because it seemed to defy expectations of how substances should behave. Today, it serves as a reminder that light can be a byproduct of instability. Radium's luminosity is a visible trace of nuclear change, making the invisible processes inside atoms briefly perceptible to the human eye. Actinium begins a sequence of heavy radioactive transformations. Actinium marks the start of a chain of transformations involving some of the heaviest elements known. Its atoms are unstable, and their decay sets off a sequence of changes that produce a series of new nuclei. Each step releases energy and particles gradually moving toward more stable configurations. This cascade reveals how heavy elements evolve over time, not through chemistry, but through nuclear restructuring. Actinium's role at the beginning of this sequence makes it a key reference for studying radioactive processes. By tracing the products that follow actinium, scientists can map how matter sheds excess energy and mass. Actinium shows that the periodic table is not static. Some elements exist primarily as waypoints, marking stages in an ongoing journey, rather than endpoints. It highlights the dynamic nature of heavy matter and the long timescales over which it transforms. Thorium could power civilizations for centuries. Thorium contains vast stores of potential energy locked within its nucleus. Under the right conditions, thorium can be converted into a form that sustains controlled nuclear reactions, releasing energy steadily rather than explosively. This process generates heat that can be used to produce electricity with minimal emissions and long-lasting fuel supplies. Thorium is relatively abundant compared to some other nuclear materials, and its reactions produce less longevity waste. These qualities have drawn deep interest to thorium as a potential source of future energy. Beyond its engineering promise, thorium reflects a wider truth hidden within the periodic table. Some elements carry quiet potential that remains dormant until human understanding and technology are ready to awaken it. For now, thorium rests calmly among the heavy metals, holding possibilities that have yet to fully unfold. Yet within it lies the capacity to reshape how energy is generated on a planetary scale. Protactinium exists in only fleeting, measurable quantities. Protactinium is one of those elements that almost slips through the cracks of observability. It appears naturally only as a short-lived product of radioactive decay, forming briefly before transforming again into something else. Because of this, protactinium never accumulates in meaningful amounts. Its atoms are scattered thinly and vanish quickly, making them extremely difficult to isolate. For a long time, this scarcity meant that protactinium remained poorly understood compared to its neighbors. When scientists finally managed to study it in more detail, they found an element whose chemistry reflects its position at a crossroads between stability and decay. Protactinium can form compounds, but its radioactivity complicates everything it touches. Its heat output
Structural instability and constant transformation blur the line between substance and process. Protactinium reminds us that the periodic table includes elements whose defining feature is not what they are, but how briefly they remain that way. It exists just long enough to teach us about the transition from order to transformation inside heavy nuclei. Uranium stores energy left over from stellar explosions. Uranium owes its existence to some of the most violent events in the universe. Its atoms were forged in extreme cosmic environments, where enormous numbers of neutrons were driven into nuclei in a very short time.
These conditions occur during catastrophic stellar events,
where matter is exposed to intense fluxes of energy and particles. The resulting uranium nuclei carry within them a surplus of energy locked into their structure. This energy remains trapped for immense spans of time, released only when the nucleus finally rearranges. On Earth, this stored energy becomes accessible through carefully managed processes that convert nuclear rearrangement into heat. Uranium thus acts as a fossil fuel of a very different kind, preserving the energetic imprint of ancient cosmic violence. Its presence connects planetary geology to stellar death, linking the deep past of the universe to modern technology. Uranium demonstrates that some elements are not just matter, but long-term energy reservoirs shaped by events far beyond our planet. Neptunium was the first element beyond uranium discovered.
Neptunium holds a special place as the first confirmed step beyond the natural endpoint of longeved elements. It does not appear in significant amounts in nature because its atoms decay away relatively quickly. Its discovery showed that the periodic table did not stop where nature seemed to stop. By inducing nuclear reactions, scientists revealed that heavier elements could exist, even if only briefly. Neptunium's chemistry reflects its heavy nucleus, with electrons influenced by strong nuclear charge and relativistic effects. Studying neptunium helped establish patterns that would later guide the search for even heavier elements. It provided proof that the table could be extended through human intervention, transforming the periodic table from a static catalogue into an expandable framework. Neptunium marks the moment when chemistry crossed into deliberate nuclear creation, opening a new frontier where elements are produced rather than found. Plutonium reshaped both physics and geopolitics. Plutonium is an element whose impact reaches far beyond laboratories. Its nucleus can undergo reactions that release enormous amounts of energy, making it central to both power generation and weapons technology. This dual capability placed plutonium at the heart of some of the most consequential scientific and political decisions in history. From a physics perspective, plutonium challenged understanding of nuclear behavior, revealing complex phase changes and unusual structural properties. From a global perspective, it altered power balances and security strategies. Plutonium's chemistry is equally complex, with multiple forms that differ dramatically in density and reactivity. These shifting states make it difficult to handle and study, adding to its mystique and danger. Plutonium demonstrates how an element can influence not only matter, but history itself. It is a reminder that scientific discoveries do not exist in isolation. They ripple out, shaping societies and decisions on a planetary scale. Americium detects dangers humans cannot sense. Americium has found a role as a silent sentinel. Its radioactive emissions can be detected reliably, making it useful for sensing conditions that would otherwise go unnoticed. In certain devices, americium acts as a constant source of particles that interact with their surroundings in predictable ways. When that interaction is disrupted, the change signals the presence of a threat. Americium's usefulness lies in consistency rather than intensity. It emits radiation steadily, allowing small deviations to stand out clearly. This makes it well suited for monitoring environments where early warning is essential. Americium's existence also highlights how radioactive elements can be harnessed safely when their behavior is well understood. The element transforms invisible risks into detectable signals, extending human perception beyond natural limits. Americium shows that some elements earn their place not through abundance or strength, but through reliability and sensitivity. Curium releases heat through radioactive decay. Curium is an element that generates warmth from within. As its atoms decay, they release energy that manifests as heat. This heat production is steady and predictable, driven by nuclear transformations rather than chemical reactions. Because of this, curium has been studied as a potential power source for environments where sunlight and conventional fuels are unavailable. Its ability to produce heat without combustion makes it valuable for applications that require long-lasting, maintenance-free energy. Curium's heat is a direct consequence of instability at the nuclear level, where excess energy is gradually shed. Studying curium helps scientists understand how heavy nuclei relax over time, and how that relaxation can be harnessed. The element illustrates a broader principle that decay is not merely loss. It can be a source of useful energy when guided properly. Curium turns transformation into warmth, quietly converting nuclear change into usable output. The helilium exists primarily to study heavier elements. The helilium is rarely encountered outside research environments, and that is largely by design. Its primary value lies not in its own applications, but in its role as a stepping stone to even heavier elements. The helilium's atoms can be used as targets in experiments where they are bombarded with particles to create new, heavier nuclei. This makes helium a gateway rather than a destination. Its own properties are difficult to study due to radioactivity and scarcity. Yet it provides essential insight into how nuclei behave as they grow larger. Producing helium requires careful control and significant effort, underscoring how far removed it is from everyday matter. Helium exemplifies the idea that some elements exist mainly to enable discovery. They are tools for exploration, allowing scientists to push the boundaries of the periodic table and test theories about nuclear structure. Californium emits neutrons with remarkable intensity. Californium is notable for its ability to release large numbers of neutrons. These neutrons emerge as a result of its nuclear decay processes, providing a powerful and concentrated source of particles that can penetrate deeply into materials. This property makes californium extremely useful in scientific and industrial applications where neutron radiation is needed. Neutrons can probe the interior of objects, trigger specific reactions, and help analyze material composition. Californium's neutron output is intense enough that very small amounts can be effective. This efficiency highlights how nuclear properties can amplify influence far beyond mass or volume. Californium's behavior also demands respect, as uncontrolled exposure carries serious risks. The element demonstrates how the periodic table extends into realms where particles themselves become tools, and where matter interacts through forces that reach far beyond chemical bonds. Einsteinium can only be studied in microscopic amounts. Einsteinium is so rare and short-lived that it can never be handled in visible quantities. It is produced in minute amounts, through complex nuclear processes and decays rapidly into other elements. Every experiment involving Einsteinium must be designed around scarcity. Scientists work with traces measured in tiny fractions, extracting information from minimal signals. Despite these challenges, Einsteinium has provided valuable insight into the behavior of very heavy atoms. Its chemistry reveals how electrons arrange themselves under extreme nuclear charge, testing theories that cannot be examined using lighter elements. Einsteinium's existence proves that knowledge does not require abundance. Even the smallest samples can illuminate fundamental principles when studied carefully. The element embodies the idea that discovery often happens at the edge of detectability, where patience and precision replace direct observation. Fermium forms during the most extreme nuclear reactions. Fermium is created only under conditions where nuclei are subjected to overwhelming numbers of neutrons in very short timescales. These conditions occur in the most extreme nuclear reactions, where matter is forced far beyond its usual limits. Fermium does not accumulate naturally because its atoms decay too quickly to persist. Each appearance is brief, marking the aftermath of intense nuclear events. Studying fermium helps scientists understand how nuclei behave when pushed to extremes, revealing how stability erodes as size increases. Fermium's properties test the boundaries of nuclear models, offering clues about how matter transitions from structured nuclei toward fragmentation. The element stands as a testament to the violence required to reach the far end of the periodic table. Fermium shows that some forms of matter can exist only in moments of extraordinary intensity. Protactinium exists in only fleeting, measurable quantities. Protactinium is one of those elements that almost slips through the cracks of observability. It appears naturally only as a short-lived product of radioactive decay, forming briefly before transforming again into something else. Because of this, protactinium never accumulates in meaningful amounts. Its atoms are scattered thinly and vanish quickly, making them extremely difficult to isolate. For a long time, this rarity left protactinium far less understood than the elements around it. When scientists were finally able to study it more closely, they discovered an element whose chemistry sits at a delicate crossroads between stability and decay. Protactinium can form compounds, yet its persistent radioactivity adds complexity to every interaction, quietly shaping how it behaves and how it must be handled. Its heat output, structural instability, and constant transformation blur the line between substance and process. Protactinium reminds us that the periodic table includes elements whose defining feature is not what they are, but how briefly they remain that way. It exists just long enough to teach us about the transition from order to transformation inside heavy nuclei. Uranium stores energy left over from stellar explosions. Uranium owes its existence to some of the most violent events in the universe. Its atoms were forged in extreme cosmic environments where enormous numbers of neutrons were driven into nuclei in a very short time. These conditions occurred during catastrophic stellar events, where matter is exposed to intense fluxes of energy and particles. The resulting uranium nuclei carry within them a surplus of energy locked into their structure. This energy remains trapped for immense spans of time, released only when the nucleus finally rearranges. On Earth, this stored energy becomes accessible through carefully managed processes that convert nuclear rearrangement into heat. Uranium thus acts as a fossil fuel of a very different kind, preserving the energetic imprint of ancient cosmic violence. Its presence connects planetary geology to stellar death, linking the deep past of the universe to modern technology. Uranium demonstrates that some elements are not just matter,
but long-term energy reservoirs shaped by events far beyond our planet. Neptunium was the first element beyond uranium discovered. Neptunium holds a special place as the first confirmed step beyond the natural endpoint of long-lived elements. It does not appear in significant amounts in nature because its atoms decay away relatively quickly.
Its discoveries showed that the periodic table did not stop where nature seemed to stop. By inducing nuclear reactions, scientists revealed that heavier elements could exist, even if only briefly. Neptunium's chemistry reflects its heavy nucleus, with electrons influenced by strong nuclear charge and relativistic effects. Studying neptunium helped establish patterns that would later guide the search for even heavier elements. It provided proof that the table could be extended through human intervention, transforming the periodic table from a static catalog into an expandable framework. Neptunium marks the moment when chemistry crossed into deliberate nuclear creation, opening a new frontier where elements are produced rather than found. Plutonium reshaped both physics and geopolitics. Plutonium is an element whose impact reaches far beyond laboratories. Its nucleus can undergo reactions that release enormous amounts of energy, making it central to both power generation and weapons technology. This dual capability placed plutonium at the heart of some of the most consequential scientific and political decisions in history. From a physics perspective, plutonium challenged understanding of nuclear behavior, revealing complex phase changes and unusual structural properties. From a global perspective, it altered power balances and security strategies. Plutonium's chemistry is equally complex, with multiple forms that differ dramatically in density and reactivity. These shifting states make it difficult to handle and study, adding to its mystique and danger. Plutonium demonstrates how an element can influence not only matter, but history itself. It is a reminder that scientific discoveries do not exist in isolation. They ripple outward, shaping societies and decisions on a planetary scale. Americium detects dangers humans cannot sense. Americium has found a role as a silent sentinel. Its radioactive emissions can be detected reliably, making it useful for sensing conditions that would otherwise go unnoticed. In certain devices, americium acts as a constant source of particles that interact with their surroundings in predictable ways. When that interaction is disrupted, the change signals the presence of a threat. Americium's usefulness lies in consistency rather than intensity. It emits radiation steadily, allowing small deviations to stand out clearly. This makes it well-suited for monitoring environments where early warning is essential. Americium's existence also highlights how radioactive elements can be harnessed safely when their behavior is well understood. The element transforms invisible risks into detectable signals, extending human perception beyond natural limits. And that shows that some elements earn their place not through abundance or strength, but through reliability and sensitivity. Curium releases heat through radioactive decay. Curium is an element that generates warmth from within. As its atoms decay, they release energy that manifests as heat. This heat production is steady and predictable, driven by nuclear transformations rather than chemical reactions. Because of this, curium has been studied as a potential power source for environments where sunlight and conventional fuels are unavailable. Its ability to produce heat without combustion makes it valuable for applications that require long-lasting, maintenance-free energy. Curium's heat is a direct consequence of instability at the nuclear level, where excess energy is gradually shed. Studying curium helps scientists understand how heavy nuclei relax over time and how that relaxation can be harnessed. The element illustrates a broader principle that decay is not merely loss. It can be a source of useful energy when guided properly. Curium turns transformation into warmth, quietly converting nuclear change into usable output. The chelium exists primarily to study heavier elements. The helilium is rarely encountered outside research environments, and that is largely by design. Its primary value lies not in its own applications, but in its role as a stepping stone to even heavier elements. Beryllium's atoms can be used as targets in experiments where they are bombarded with particles to create new, heavier nuclei. This makes beryllium a gateway rather than a destination. Its own properties are difficult to study due to radioactivity and scarcity, yet it provides essential insight into how nuclei behave as they grow larger. Producing beryllium requires careful control and significant effort, underscoring how far removed it is from everyday matter. The helium exemplifies the idea that some elements exist mainly to enable discovery. They are tools for exploration, allowing scientists to push the boundaries of the periodic table and test theories about nuclear structure. Californium emits neutrons with remarkable intensity. Californium is notable for its ability to release large numbers of neutrons. These neutrons emerge as a result of its nuclear decay processes, providing a powerful and concentrated source of particles, but can penetrate deeply into materials. This property makes californium extremely useful in scientific and industrial applications where neutron radiation is needed. Neutrons can probe the interior of objects, trigger specific reactions, and help analyze material composition. Californium's neutron output is intense enough that very small amounts can be effective. This efficiency highlights how nuclear properties can amplify influence far beyond mass or volume. Californium's behavior also demands respect, as uncontrolled exposure carries serious risks. The element demonstrates how the periodic table extends into realms where particles themselves become tools, and where matter interacts through forces that reach far beyond chemical bonds. Einsteinium can only be studied in microscopic amounts. Einsteinium is so rare and short-lived that it can never be handled in visible quantities. It is produced in minute amounts through complex nuclear processes and decays rapidly into other elements. Every experiment involving Einsteinium must be designed around scarcity. Scientists work with traces measured in tiny fractions, extracting information from minimal signals. Despite these challenges, Einsteinium has provided valuable insight into the behavior of very heavy atoms. Its chemistry reveals how electrons arrange themselves under extreme nuclear charge, testing theories that cannot be examined using lighter elements. Einsteinium's existence proves that knowledge does not require abundance. Even the smallest samples can illuminate fundamental principles when studied carefully. The element embodies the idea that discovery often happens at the edge of detectability, where patience and precision replace direct observation. Fermium forms during the most extreme nuclear reactions. Fermium is created only under conditions where nuclei are subjected to overwhelming numbers of neutrons in very short timescales. These conditions occur in the most extreme nuclear reactions, where matter is forced far beyond its usual limits. Fermium does not accumulate naturally because its atoms decay too quickly to persist. Each appearance is brief, marking the aftermath of intense nuclear events. Studying fermium helps scientists understand how nuclei behave when pushed to extremes, revealing how stability erodes as size increases. Fermium's properties test the boundaries of nuclear models, offering clues about how matter transitions from structured nuclei toward fragmentation. The element stands as a testament to the violence required to reach the far end of the periodic table. Fermium shows that some forms of matter can exist only in moments of extraordinary intensity. Mendelevium honors the logic behind the periodic table itself. Mendelevium carries a significance that goes beyond its physical properties. It stands as a tribute to the idea that matter follows patterns that can be predicted before they are observed. Long before Mendelevium was ever produced, its place was implied by the structure of the periodic table. Its eventual creation confirmed that the table was not merely descriptive, but genuinely predictive. Mendelevium's atoms are unstable and short-lived, yet their existence validates the underlying logic that organizes all elements. Studying Mendelevium helps scientists test whether theoretical models of atomic structure hold true at extreme sizes and charges. Its chemistry, though difficult to explore in detail, reflects trends anticipated by its position. Mendelevium thus represents a rare moment where human reasoning about nature was confirmed by nature itself. It shows that the periodic table is not a static list, but a framework capable of pointing toward realities that had not yet been reached. Mendelevium embodies confidence in order, even at the far edges of matter. Mendelevium challenged early predictions of atomic structure. Mendelevium did not behave quite as expected when scientists first began to study it. Early theoretical models predicted certain chemical properties based on its position in the periodic table, but experimental results hinted at surprises. These discrepancies forced researchers to revisit assumptions about how electrons arrange themselves in very heavy atoms. In noble metals and lighter elements, patterns are relatively clear. In elements like nobelium, the intense nuclear charge alters electron behavior in subtle but important ways. Nobelium helped reveal that predictions become harder as atoms grow larger and relativistic effects begin to matter more. Its study refined theoretical approaches and improved understanding of how atomic structure evolves across the table. Nobelium's value lies not in usefulness, but in correction. It showed where ideas needed adjustment, reminding scientists that even well-established frameworks must remain flexible. Through nobelium, the periodic table proved strong enough to withstand revision rather than collapse under it. Luranium blurs the boundary between element families. Luranium sits at a crossroads where classifications begin to lose sharpness. Its properties do not fit neatly into a single family, making it difficult to categorize using traditional rules. This ambiguity arises because luranium's electrons are influenced by competing forces that reshape expected behavior. The balance between nuclear charge and electron arrangement shifts enough that familiar trends become unreliable. Studying lawrencium has helped scientists understand how element families gradually transition rather than ending abruptly. It shows that the periodic table is not divided by rigid walls, but by regions where identity slowly changes. Luranium's behavior challenges simple labels and encourages a more nuanced view of atomic organization. It reminds us that nature often resists clean boundaries. Luranium exists in the gray zones of classification, where understanding comes not from fitting elements into boxes, but from recognizing continuity across the table. Ruthenium tests the limits of nuclear stability. Ruthenium lies in a region where nuclei are pushed to extremes. Its atoms are large, heavily charged, and inherently unstable, making their survival a delicate balance. Creating ruthenium requires precise conditions, and once formed, its atoms exist only briefly before decaying. Studying ruthenium allows scientists to explore how nuclear forces compete as size increases. The strong nuclear force must bind together an ever-increasing number of protons that naturally repel one another through electrical charge. Rutherfordium reveals just how close matter can come to breaking apart while still holding on to a recognizable atomic identity. Its behavior helps scientists refine their understanding of nuclear binding and radioactive decay. Rutherfordium does not contribute to materials or biology. Its true value lies in testing theory, probing the limits of how atoms can exist at all. It marks a point where stability becomes rare and temporary, illuminating the boundaries that define how heavy an element can realistically be. Dugnium exists for only fractions of a moment. Dugnium is an element defined almost entirely by its disappearance. Once created, its atoms decay so quickly that their presence must be inferred from chains of transformation rather than direct observation. Each atom exists only long enough to leave a signature before becoming something else. This fleeting existence makes dugnium more like a brief signal than a substance. Yet even such short-lived matter can reveal meaningful information. By tracking how dugnium decays, scientists can confirm its identity and learn about the forces shaping heavy nuclei. Dugnium demonstrates that duration is not a requirement for significance. Even momentary existence can test theories and extend understanding. The periodic table includes these ephemeral entries to acknowledge possibilities, not permanence. Dugnium shows that matter can exist on timescales far shorter than human perception and still be real, measurable, and informative. Seborgium confirmed predictions made decades earlier. Seborgium occupies a place that scientists had anticipated long before they could produce it. Its eventual creation served as a confirmation that theoretical predictions about heavy elements were sound. Seborgium's behavior aligned closely with expectations based on periodic trends, reinforcing confidence in the table's organizing principles. This agreement was not guaranteed, especially given the complexities introduced by large nuclei and relativistic effects. Seborgium's chemistry and decay patterns provided reassurance that the logic governing lighter elements still applied, at least in part, at much higher atomic weights. Its existence helped bridge the gap between theory and experiment in the realm of superheavy elements. Seborgium stands as evidence that careful reasoning can reach far beyond immediate observation. It reinforces the idea that the periodic table remains a reliable guide, even as scientists push toward its outermost edges. Orium decays faster than it can be fully observed. Orium is so unstable that studying it feels like chasing a vanishing point. Its atoms decay almost immediately after formation, limiting how much information can be gathered. Experiments must be designed to extract maximum insight from minimal time. Each decay event becomes valuable data. Orium's rapid transformation highlights how quickly nuclear instability can dominate behavior. Chemical interactions become almost irrelevant when nuclei cannot persist long enough to engage meaningfully. Yet even this extreme instability teaches important lessons. BIM helps scientists understand how decay pathways change as nuclei grow heavier and more charged. It shows how predictability fades near the limits of matter. Barium's presence on the periodic table acknowledges not usefulness, but completeness. It represents the far reach of what can exist, even briefly, under the rules of nuclear physics. Him mimics lighter elements in unexpected ways. Hum displays behavior that seems surprisingly familiar despite its extreme weight. In some reactions, it behaves similarly to much lighter elements in its group, following trends that appear to hold even under intense nuclear charge. This mimicry suggests that certain chemical patterns remain robust across vast differences in atomic size. Hassium's ability to echo lighter behavior provides valuable insight into how electron structure persists even as nuclei become enormous. At the same time, subtle deviations reveal where those patterns begin to break down. Hassium thus serves as both confirmation and test. It shows where chemistry remains predictable and where new effects emerge. Studying hassium helps clarify how far periodic trends can be trusted. It reminds us that even at the edges, matter sometimes behaves in recognizable ways, offering continuity amid extremity. Magnarium exists only through advanced particle collisions. Magnarium does not appear naturally in any lasting form. It must be created through carefully orchestrated particle collisions that push nuclei into contact with immense precision. These events occur one atom at a time, each creation requiring extraordinary effort. Once formed, Newtonarium decays quickly, leaving behind evidence of its brief existence. Its production relies on deep understanding of nuclear reactions, beam control, and detection methods. Magnarium's study reveals how far technology has advanced in probing matter. It represents the ability to reach into realms that nature does not sustain on its own. Martinarium's value lies in demonstrating control rather than application. It shows that humans can explore possibilities beyond natural abundance, extending the periodic table into domains defined by ingenuity rather than geology. DM Statium pushes experimental chemistry to its limits. Donstatium is one of the most challenging elements to study because of its extreme instability and rarity. Creating even a few atoms requires prolonged experiments and precise conditions. Once formed, these atoms decay almost immediately, offering only fleeting glimpses of their behavior. Extracting chemical information under such constraints pushes experimental techniques to their limits. Researchers must rely on indirect measurements, rapid detection, and statistical confidence. DM Statium tests not only theories of atomic structure, but also the ingenuity of experimental design. Its existence confirms that the periodic table extends into regions where observation becomes an art of inference. Darmstadium represents the frontier, where chemistry approaches pure physics and where patience replaces abundance. It marks how far the exploration of matter can go before time itself becomes the limiting factor. Rontoinium reveals how heavy atoms bend physical rules. Rontoinium exists in a realm where the usual expectations of chemistry begin to warp. Its nucleus is so strongly charged that electrons orbiting it are forced into extreme behavior. These electrons move at speeds where relativistic effects become significant, altering their mass and energy in measurable ways. As a result, Rontoinium's chemical behavior cannot be predicted simply by extrapolating from lighter elements. Properties such as bonding strength, reactivity, and stability are reshaped by physics. Normally associated with stars and black holes rather than laboratory benches, studying Rontogenium helps scientists understand how fundamental laws interact when pushed to extremes. It shows that the periodic table is not governed by chemistry alone, but by a fusion of quantum mechanics and relativity. Runtogenenium demonstrates that as atoms grow heavier, they begin to obey a different balance of rules, revealing limits to intuition built from everyday matter. Copernesium behaves unlike any metal before it. Copanium challenges the very idea of what it means to be a metal. Although it sits among metallic elements on the periodic table, its predicted behavior suggests it may act more like a volatile substance than a solid conductor. Relativistic effects strongly influence its electrons, stabilizing certain orbitals and weakening metallic bonding. This effect can weaken the bonds between atoms, potentially leaving copernicium far less solid than the elements around it. Because the element exists only for fleeting moments, direct observation remains extremely challenging. Yet, theoretical models suggest behaviors that resist easy classification, hinting at properties that blur the familiar boundaries of how matter is expected to behave. Cupesium blurs the line between metal and non-metal, showing that periodic trends can bend sharply at high atomic numbers. It serves as a reminder that categories used for lighter elements are not guaranteed to hold indefinitely. Copenium invites a rethinking of how metallic behavior arises and where it may ultimately fail. Nonium represents a rare achievement in element discovery. Nonium stands as a symbol of perseverance and precision in scientific discovery. Its creation required carefully tuned experiments where atomic nuclei were brought together under exact conditions, producing just a few atoms that existed for moments before decaying. Detecting those atoms demanded sensitive instruments and rigorous confirmation. Nonium's recognition marked a milestone, not only because of its position on the periodic table, but because of the collaborative effort behind it. It demonstrated that element discovery had become a global enterprise, requiring shared expertise and patience. Mahonium's existence confirms that the periodic table can still grow, even as it approaches its limits. It represents the culmination of theoretical prediction, experimental mastery, and verification. Mahonium shows that discovery at the frontiers of matter is no longer about chance, but about sustained, deliberate exploration. Fluovium challenges assumptions about atomic shells. Fluorovium occupies a region where traditional models of atomic structure begin to strain. Its electrons are arranged under the influence of an enormous nuclear charge, which alters shell structure in unexpected ways. Some predictions suggest that fluorovium's outer electrons may be more tightly bound than anticipated, potentially granting it unusual stability. This behavior contrasts with expectations based on lighter elements in the same group. Fluovium thus provides a test case for how electron shells evolve under extreme conditions. Studying it helps refine theories about how electrons organize themselves when relativistic effects dominate. Ferrovium shows that atomic shells are not rigid frameworks, but adaptable structures shaped by competing forces. It reveals how the periodic table remains dynamic, even at its farthest reaches. Moscovium exists at the edge of detectability. Moscovium's atoms appear only briefly and in vanishingly small numbers. Each creation event must be inferred from decay patterns rather than direct observation. This places Moscow at the threshold where existence itself becomes difficult to confirm. Experiments designed to study it must extract meaning from minimal data, relying on statistical confidence and careful elimination of alternatives. Moscow's fleeting nature makes it a challenge not only to chemistry, but to measurement itself. Its study highlights how scientific knowledge can be built even when direct access is impossible. Moscow exists at the boundary where matter flickers into being just long enough to leave a trace. It represents how far the periodic table extends into realms defined by probability rather than permanence. Liverorium shows hints of surprising stability. Liverorium occupies a region where extreme instability is expected, yet some of its isotopes persist slightly longer than anticipated. These hints of stability suggest that certain arrangements of protons and neutrons can resist decay even at very high atomic numbers. This behavior has fueled interest in the idea that islands of relative stability
may exist among super-heavy elements.
Livermorium's properties help refine predictions about where such regions might lie. Its study reveals that nuclear stability does not decrease smoothly, but can fluctuate due to subtle structural effects. Livermore demonstrates that even near the limits of matter, order can briefly emerge. It offers a glimpse of how nuclei may find temporary balance against overwhelming forces. Tennessine may behave unlike any H halogen before it. Tennessine sits where the familiar behavior of H halogens begins to dissolve. While lighter H halogens are highly reactive nonmetals, Tennessine's heavy nucleus and relativistic electron effects may produce very different chemistry. Predictions suggest that it could display metallic or semi-metallic traits, rather than the aggressive reactivity typical of its group. This shift would represent a dramatic departure from periodic expectations. Tennessine thus serves as a test of how group identity holds up under extreme conditions. Its behavior may reshape what it means to belong to a chemical family. Tennessine reminds us that periodic trends are gentle guides rather than fixed rules, and that entirely new behaviors can emerge when atomic structure is pushed to its limits. Oganesson goes even further, stretching the very definition of what an element can be, quietly challenging our understanding of matter itself. Essence stands at the current end of the periodic table where conventional descriptions begin to fail. Its atoms are so heavy and short-lived that many of the usual assumptions about elements may not apply. Predictions suggest that Oganesson may not behave like a typical noble gas at all, possibly forming weak bonds or existing in unusual states. Its electron cloud is profoundly affected by relativistic effects reshaping how it interacts with its surroundings. Oganesson challenges the notion that elements are stable substances with well-defined properties. Instead, it suggests that at the extreme edge, elements become transient configurations, governed as much by physics as by chemistry. Oganesson marks the point where the periodic table transitions from a map of materials to a map of possibilities, showing how far the concept of an element can be stretched before it dissolves into pure theory. As our quiet journey through the periodic table comes to a close, you may notice how the world around you feels a little deeper, a little more layered than before. Every breath, every surface, every distant star is built from the same small set of possibilities, arranged and rearranged by rules that are both strict and surprisingly poetic. What once looked like a grid of symbols is now a long story of endurance, instability, rarity, and change. These elements do not rush. They take their time. Some persist for billions of years. Others appear only briefly, leaving behind faint signatures before fading away. Together, they remind us that the universe is not hurried, and neither are you required to be. Complexity can arise slowly. Balance can be found without force. If you enjoyed drifting through this landscape of matter, I invite you to like the video, subscribe to the channel, or leave a gentle thought below. It helps others discover this quiet space too, one curious mind at a time. But for now, there is nothing left to learn and nowhere left to go. Let the names and ideas soften and blur. Let your breathing slow. Allow the weight of the day to settle and dissolve, just as atoms settle into their most comfortable arrangements. You are part of this story too. Made from ancient pieces that have traveled an unimaginably long way to become you. And now, it is time to rest. Good night.